Imagine a place in space where invisible forces clash, creating a protective shield that guards an entire planet. A place where particles from the Sun, traveling at millions of miles per hour, collide with an unseen yet incredibly powerful barrier, forming a dynamic battleground. This is the magnetopause, a mysterious frontier at the edge of Earth's magnetic field, where the solar wind meets the planet's defenses. What exactly is happening in this enigmatic region, and why does it matter so much for life on Earth? Stay with me as we dive into the story of the magnetopause, uncovering the secrets of this unseen shield that plays a role in everything from the breathtaking auroras in the night sky to the very survival of life as we know it. To understand the magnetopause, we first need to set the stage with a basic question: what is the solar wind, and why does it need to be stopped? The Sun, our star, is far more than just a glowing ball in the sky. It's a colossal nuclear engine constantly releasing streams of charged particles known as the solar wind. This wind isn't like the breeze you feel on Earth. It's a high-speed river of protons and electrons, sometimes gusting at speeds of over 1,000,000 miles per hour. It carries with it an invisible but powerful magnetic field, and when it reaches Earth, it slams into another magnetic field, our planet's own. Earth's magnetic field originates deep within its core. The swirling, molten iron at the center of the planet creates a dynamo effect, generating a magnetic field that extends far into space. This magnetic bubble, called the magnetosphere, acts like a shield, deflecting most of the harmful solar wind away from the planet. But where these two forces meet, the solar wind and the magnetosphere, is where things get really interesting. That's the magnetopause, a turbulent and ever-shifting boundary that protects us while also revealing the raw power of the cosmos. The magnetopause isn't a solid wall. Think of it more like the surface of a soap bubble being pressed on one side. The solar wind pushes against Earth's magnetic field, compressing it on the day side, the side facing the Sun, and stretching it out on the night side, forming a long magnetic tail called the magnetotail. This interaction creates a highly dynamic and complex region where magnetic fields snap, reconnect, and release bursts of energy. But why does this matter to us down here on the surface? Well, the magnetopause is like the Earth's first line of defense. Without it, the solar wind would strip away our atmosphere over time, just like what happened on Mars. Mars once had a magnetic field, but when its core cooled and the field disappeared, the solar wind gradually eroded its atmosphere, leaving the planet cold, dry, and barren. Earth's magnetopause ensures that doesn't happen here. What's even more fascinating is that the magnetopause isn't a static structure. It's constantly in flux, responding to changes in the solar wind. When a solar storm, a sudden outburst of energy from the Sun, hits the magnetopause, it can push it closer to Earth. This compression can cause disruptions to satellites, power grids, and communication systems. But it can also create spectacular displays of auroras, as charged particles are funneled along magnetic field lines into Earth's atmosphere, where they collide with atoms and molecules to create shimmering lights in the sky. Let's dig deeper into how this boundary works. The magnetopause is essentially a region of pressure balance. On one side you have the pressure of the solar wind, on the other, the pressure of Earth's magnetic field. The exact location of the magnetopause depends on the strength of these forces. During periods of intense solar activity, the magnetopause can be pushed closer to Earth, while during quieter times, it can expand farther out into space. Scientists have calculated that, on average, the magnetopause is located about 10 Earth radii away from the planet on the day side. One of the most fascinating phenomena that occur at the magnetopause is magnetic reconnection. This is a process where the magnetic fields of the solar wind and Earth's magnetosphere connect and realign, releasing enormous amounts of energy. Magnetic reconnection is not just an earthly phenomenon. It happens throughout the universe, in stars, in galaxies, and even in black holes. But here at the magnetopause, it plays a crucial role in transferring energy and particles into the magnetosphere, fueling the auroras and driving space weather. Studying the magnetopause isn't just about understanding Earth's defenses. It's also about preparing for the future. As we become more reliant on technology, from GPS to power grids, understanding how solar storms interact with the magnetopause is critical. A powerful enough storm could cause catastrophic disruptions, knocking out satellites and even disabling electrical systems on the ground. By studying the magnetopause, scientists can develop better models to predict space weather and protect our technological infrastructure. The magnetopause also holds clues to the behavior of plasmas, the fourth state of matter. Unlike solids, liquids, or gases, plasmas are charged particles that respond to magnetic and electric fields. The magnetopause is essentially a giant natural laboratory for studying plasmas, helping scientists understand everything from solar flares to the behavior of plasma in fusion reactors on Earth. As we continue to explore space, understanding the magnetopause takes on new importance. Future missions to the Moon, Mars, and beyond will need to contend with the solar wind and its effects. While Earth's magnetic field protects us here, astronauts venturing into deep space won't have that luxury. By studying how the magnetopause interacts with the solar wind, scientists can develop better shielding technologies to protect future space travelers. The magnetopause isn't just a boundary, it's a story of cosmic forces colliding, a dance of magnetic fields and charged particles that shapes the environment of our planet. It's a reminder that even the invisible forces of the universe play a crucial role in our everyday lives. The next time you see an aurora or use your GPS, think about the magnetopause, quietly working behind the scenes to keep our world habitable. And remember, the mysteries of space are not just out there, they're happening right here, at the edge of our planet's magnetic field. The magnetopause is not just a passive structure, it's a highly dynamic region, constantly responding to the sun's whims. Let's explore its ever-changing nature and how its behavior affects us. To understand this better, imagine a rubber band stretched taut, vibrating with the slightest touch. The magnetopause behaves in a similar way, responding to variations in the solar wind with shifts, ripples, and fluctuations that ripple through the magnetosphere. One of the most intriguing phenomena observed at the magnetopause is known as Kelvin-Helmholtz waves. These are massive, rolling wave-like structures that form when the solar wind flows past the magnetopause at high speeds, creating turbulence at the boundary. Picture a fast-moving river meeting a calm lake. The chaotic interface between the two is similar to what happens at the magnetopause. These waves can grow large enough to allow solar wind particles to sneak past the magnetopause and into the magnetosphere, adding another layer of complexity to this already chaotic region. But that's just the start. The magnetopause also serves as a gateway for energetic particles. During magnetic reconnection, charged particles from the solar wind can enter the magnetosphere and become trapped within Earth's magnetic field. These particles spiral along magnetic field lines, forming regions of intense radiation known as the Van Allen radiation belts. While these belts protect us by capturing harmful particles, they also pose a hazard to satellites, astronauts, and high-altitude flights, particularly during periods of intense solar activity. The magnetopause's interaction with the solar wind isn't limited to magnetic reconnection and particle entry. It also plays a critical role in shaping Earth's magnetotail, the elongated, comet-like extension of the magnetosphere on the night side of the planet. This region acts as a reservoir of energy and particles, which can be suddenly released during geomagnetic storms. These storms, triggered by interactions at the magnetopause, can have dramatic effects, from dazzling auroras to disruptions in communication systems. To study the magnetopause, scientists rely on a combination of spacecraft observations, ground-based measurements, and sophisticated computer models. Missions like NASA's Magnetospheric Multiscale (MMS) mission have provided unprecedented insights into the fine-scale processes occurring at this boundary. The MMS spacecraft are equipped with instruments capable of measuring magnetic fields, electric fields, and particle fluxes with extreme precision. These data have revealed the intricate details of magnetic reconnection and other phenomena, shedding light on the fundamental physics at play. One of the most exciting discoveries made by MMS is the presence of tiny, transient structures called flux transfer events, FTEs. These are magnetic ropes that form during magnetic reconnection, temporarily linking the solar wind's magnetic field with Earth's. FTEs act as conduits for energy and particles, transferring them into the magnetosphere. They are like cosmic highways, bridging the gap between the Sun and Earth in a way that's both fascinating and impactful. The magnetopause also plays a key role in what scientists call space weather forecasting. Space weather refers to the conditions in space driven by solar activity, and it can have significant impacts on modern technology. For example, a strong geomagnetic storm can cause satellite malfunctions, disrupt GPS signals, and even damage power grids on the ground. By monitoring the magnetopause and its response to the solar wind, scientists can better predict space weather events and mitigate their effects. It's worth noting that the magnetopause isn't unique to Earth. Other planets with magnetic fields, like Jupiter and Saturn, also have magnetopauses. These structures vary in size and shape depending on the strength of the planet's magnetic field and its distance from the Sun. For instance, Jupiter's magnetopause is enormous, extending millions of kilometers from the planet due to its incredibly strong magnetic field. Studying these extraterrestrial magnetopauses helps scientists understand how magnetic fields interact with solar wind across the solar system and beyond. Even as we marvel at the magnetopause's role in protecting Earth, it's important to recognize that it also exposes the planet to certain risks. When magnetic reconnection occurs at the magnetopause, it can lead to what's known as geomagnetic substorms. These substorms unleash bursts of energy that travel along Earth's magnetic field lines, causing disturbances in the magnetosphere and ionosphere. While substorms are responsible for the beautiful auroras, they can also interfere with radio communications and navigation systems, posing challenges for modern technology. The magnetopause is also a critical consideration for future space exploration. As humanity plans missions to the Moon, Mars, and beyond, understanding how solar wind interacts with magnetic fields is essential. For example, lunar missions will need to account for the Moon's lack of a global magnetic field, which means it doesn't have a magnetopause to protect it. Similarly, studying the magnetopause can help scientists design better shielding technologies for spacecraft and habitats, ensuring the safety of astronauts in deep space. In recent years, there has been growing interest in exploring how the magnetopause responds to extreme space weather events. These events, often triggered by powerful solar eruptions like coronal mass ejections, CMEs, can compress the magnetopause dramatically, sometimes bringing it closer to Earth than ever before. When this happens, satellites in geostationary orbit can find themselves temporarily exposed to the solar wind, increasing the risk of damage from radiation and charged particles. Despite decades of research, the magnetopause remains a region of ongoing discovery. Scientists are still working to understand the full range of processes that occur at this boundary, from the small-scale dynamics of magnetic reconnection to the large-scale effects of space weather. Every new insight adds to our understanding of the magnetosphere as a whole, providing a clearer picture of how Earth interacts with the Sun and the broader cosmos. The magnetopause is a reminder of the interconnectedness of the universe. It's a place where forces from the Sun and Earth collide, creating a dynamic and ever-changing frontier that shapes our planet's environment. It's a shield, a gateway, and a laboratory all in one, a testament to the complexity and beauty of the cosmos. And while it may be invisible to the naked eye, its effects are felt every day, from the auroras that dance across the sky to the technology that powers our modern world. The magnetopause, often described as Earth's first line of defense against the solar wind, is a critical element of our planet's space environment. It might seem like an abstract concept, but its impacts on Earth are anything but. This invisible boundary is constantly shaping and being shaped by cosmic forces, creating a dynamic interplay that has profound consequences for everything from atmospheric processes to technological infrastructure. One fascinating aspect of the magnetopause is its shape. While often depicted as a neat, symmetrical bubble around Earth, the reality is far more complex. On the side facing the Sun, the solar wind compresses the magnetopause, creating a blunt, rounded shape. On the night side, where the solar wind exerts less direct pressure, the magnetopause extends outward into a long, trailing magnetotail. This shape is not static, it fluctuates based on solar activity, expanding during periods of calm and contracting during solar storms. These fluctuations aren't merely theoretical, they have measurable, real-world effects. For example, When the magnetopause is compressed during intense solar activity, it can expose satellites to increased radiation levels. Engineers must account for this in satellite design, adding protective measures to shield sensitive components. These measures are not just precautionary, they are essential, as satellite damage can lead to communication blackouts, loss of navigation systems, and even cascading failures in interconnected technologies on Earth. To fully appreciate the magnetopause's role, it's essential to understand its connection to the Sun. The Sun is not a static ball of fire but a dynamic star that constantly ejects streams of charged particles known as the solar wind. This wind carries with it the Sun's magnetic field, forming what scientists call the interplanetary magnetic field (IMF). When this solar wind collides with Earth's magnetic field, the interaction defines the magnetopause's boundary and dynamics. This interaction is far from gentle. The solar wind strikes the magnetopause at speeds averaging 400 km per second, though during solar storms, these speeds can reach as high as 800 km per second. The energy transfer at this boundary is immense, fueling processes like magnetic reconnection. Reconnection is not only a way for particles to breach the magnetopause but also a mechanism that converts magnetic energy into kinetic and thermal energy. This process is key to many space weather phenomena, including the auroras and geomagnetic storms. The auroras, often seen near polar regions, are one of the most visually stunning consequences of magnetopause activity. When solar wind particles enter Earth's magnetosphere, they are guided along magnetic field lines toward the poles. Here, they collide with particles in Earth's atmosphere, causing them to glow in vibrant hues of green, red, and purple. While these light shows are mesmerizing, the underlying processes are a reminder of the powerful forces at play in the magnetosphere. But there's more to the story. The magnetopause is not only a boundary but also a barrier that protects Earth from the Sun's most harmful emissions. Without this shield, the solar wind would strip away Earth's atmosphere over time, much like what likely happened to Mars. Mars, which lacks a global magnetic field, has a much thinner atmosphere than Earth, partly because it doesn't have a magnetopause to deflect the solar wind. This comparison underscores the importance of our planet's magnetic shield in maintaining the conditions necessary for life. Despite its protective role, the magnetopause is not invulnerable. During powerful solar events, such as coronal mass ejections (CMEs), the boundary can be pushed closer to Earth than usual. These events can compress the magnetosphere so much that high-altitude satellites, which are typically shielded by the magnetopause, find themselves exposed to the full force of the solar wind. This exposure can damage electronic components and disrupt satellite operations, with ripple effects for services like GPS and telecommunications. One of the most intriguing scientific questions about the magnetopause is its role in the broader heliosphere. The heliosphere is the vast bubble of space dominated by the Sun's magnetic field, and Earth's magnetosphere is just one small part of this larger structure. Understanding how the magnetopause interacts with the heliosphere could provide insights into space weather patterns, the behavior of cosmic rays, and even the conditions in interstellar space. To probe these mysteries, researchers are turning to increasingly sophisticated tools and techniques. Satellites like NASA's MMS and Europe's cluster mission are providing detailed measurements of the magnetic and electric fields at the magnetopause. Meanwhile, ground-based observatories are helping to track the effects of magnetopause activity on Earth's ionosphere and atmosphere. Together, these observations are painting a more complete picture of how this boundary operates and evolves. One area of active research is the study of plasmids, which are giant blobs of plasma that break away from the magnetotail during geomagnetic storms. These plasmids are thought to form as a result of reconnection events at the magnetopause, and they play a crucial role in the dynamics of the magnetosphere. By studying plasmids, scientists hope to better understand how energy is stored and released in Earth's magnetic environment. Another intriguing topic is the role of the magnetopause in regulating space weather impacts. By acting as a buffer, the magnetopause helps to moderate the effects of solar storms on Earth. However, this buffering capacity is not infinite. During extremely powerful storms, the magnetopause can be overwhelmed, leading to severe space weather events. Understanding the limits of this protective mechanism is critical for developing more accurate space weather forecasts. The magnetopause also has implications for human exploration of space. As we venture beyond low Earth orbit, astronauts and spacecraft will be exposed to environments where the magnetopause's protective influence is reduced or absent. For missions to the Moon, Mars, and beyond, it will be essential to develop technologies that can provide similar levels of protection against radiation and charged particles. In this context, studying the magnetopause can inform the design of these next-generation systems. Ultimately, the magnetopause is a region of contrasts. It is both a shield and a gateway, a barrier and a bridge. It protects Earth from the Sun's most harmful emissions while allowing the transfer of energy and particles that drive fascinating phenomena like the auroras. It is a reminder of the delicate balance that allows life to thrive on our planet, a balance maintained by forces that are both cosmic and profoundly local. As we continue to explore this boundary, we are not just learning about the magnetopause itself but also gaining a deeper understanding of our place in the solar system. The magnetopause is a window into the interconnectedness of space and Earth, a dynamic interface that links us to the Sun and the broader cosmos. In studying it, we are uncovering the secrets of a system that sustains and shapes our world, revealing the intricate dance of forces that define life on Earth. The magnetopause, while invisible to the naked eye, is a site of continuous activity and a testament to the dynamic nature of Earth's interactions with the cosmos. Its role in shaping our planet's environment and protecting life cannot be overstated. To appreciate its complexity, it is necessary to delve into the specifics of its composition, its mechanisms of action, and the ways in which it interacts with the surrounding regions of space. At its core, the magnetopause is not a physical structure but rather a boundary defined by the balance of forces. On one side, the solar wind exerts pressure outward, and on the other, Earth's magnetic field pushes back. This delicate equilibrium creates a transitional region where the characteristics of plasma, a superheated, ionized state of matter, change dramatically. Beyond the magnetopause lies the solar wind-dominated environment, and within it resides Earth's magnetosphere, a region controlled by the planet's magnetic field. The plasma that exists in this boundary is incredibly thin compared to Earth's atmosphere. In fact, the density of particles here is akin to the vacuum of space, yet these particles are highly energized. The energy and speed of these particles are dictated by their origins, with solar wind particles moving at hundreds of kilometers per second. These high velocities mean that the interactions at the magnetopause occur at a scale and intensity that is difficult to comprehend without advanced modeling and satellite observations. One of the most significant processes occurring at the magnetopause is magnetic reconnection. This phenomenon, though highly technical, is best understood as a kind of cosmic energy conversion. When magnetic field lines from the Sun and Earth align in opposite directions and come into close contact, they can snap and reform, releasing a tremendous amount of energy. This energy accelerates particles, causing them to penetrate deeper into Earth's magnetosphere or escape into space. Magnetic reconnection is not a random occurrence. It is influenced by the Sun's activity and the orientation of the interplanetary magnetic field. During periods of heightened solar activity, such as solar flares or coronal mass ejections, reconnection events become more frequent and intense. These periods coincide with geomagnetic storms that can disrupt power grids, damage satellites, and even pose risks to astronauts aboard the International Space Station. The energy released during reconnection events also powers Earth's auroras. These breathtaking light displays are more than just a spectacle, they are a visual manifestation of the dynamic processes at the magnetopause. When charged particles are funneled along magnetic field lines toward the polar regions, they collide with atmospheric gases, exciting the atoms and causing them to emit light. The color of the auroras depends on the type of gas involved, with oxygen producing green and red hues and nitrogen creating blue and purple shades. Auroras, while beautiful, are also a sign of the magnetopause's vulnerability during intense solar activity. When the magnetopause is compressed, it exposes regions of the magnetosphere that are typically shielded. This compression can allow an increased flux of solar wind particles to reach Earth's atmosphere, creating conditions for geomagnetic storms. These storms are not just a concern for space operations. They have direct impacts on everyday life on Earth. One major area of concern is the effect of geomagnetic storms on power grids. When the magnetopause is overwhelmed, the increased flow of charged particles induces electric currents in Earth's ionosphere. These currents can couple with ground-based systems, generating surges in power lines and transformers. In severe cases, this can lead to widespread blackouts, as was seen during the infamous Quebec blackout of 1989. Understanding the magnetopause's behavior is therefore crucial for developing strategies to mitigate these risks. In addition to its role in space weather, the magnetopause is a key player in the global circulation of energy and particles within the magnetosphere. The magnetosphere itself is divided into several regions, including the plasmasphere, the radiation belts, and the magnetotail. Each of these regions is interconnected, and the magnetopause serves as a kind of gateway that regulates the flow of particles and energy between them. The magnetotail, for instance, is an elongated region of the magnetosphere that stretches away from the Sun. It is here that much of the energy from reconnection events is stored and later released in explosive bursts known as substorms. These substorms not only energize particles within the magnetosphere but also contribute to the dynamic behavior of the auroras, creating rapid, flickering displays that can be observed from the ground. The plasmasphere, located closer to Earth, is another region influenced by the magnetopause. This donut-shaped area contains colder, denser plasma that originates from Earth's ionosphere. The boundary between the plasmasphere and the surrounding magnetosphere, known as the plasmapause, is shaped by the forces at the magnetopause. During periods of high solar activity, the plasmapause can erode, allowing particles from the plasmasphere to escape into the magnetosphere and participate in larger-scale dynamics. The radiation belts, also known as the Van Allen belts, are yet another component of the magnetosphere that is affected by the magnetopause. These belts contain highly energetic particles that are trapped by Earth's magnetic field. When the magnetopause is compressed, it can cause the radiation belts to become more energized, posing increased risks to satellites and other space-based technologies. Engineers must account for these variations when designing spacecraft, ensuring they can withstand the harsh conditions of space. Understanding the magnetopause also has implications for planetary science beyond Earth. Other planets in the solar system, such as Jupiter and Saturn, have their own magnetospheres and magnetopauses, shaped by their unique magnetic fields and interactions with the solar wind. By studying Earth's magnetopause, scientists can draw comparisons and gain insights into the behavior of these distant worlds. In fact, some planets, like Venus and Mars, lack a global magnetic field altogether. As a result, they do not have a magnetopause and are directly exposed to the solar wind. This exposure has profound implications for their atmospheres. Mars, for example, has lost much of its original atmosphere due to the relentless stripping effects of the solar wind. This stark contrast highlights the vital role that Earth's magnetopause plays in preserving the planet's habitability. Despite the progress made in understanding the magnetopause, many questions remain. For example, researchers are still working to unravel the details of how reconnection events are triggered and how they evolve over time. Advanced computer models and simulations are helping to shed light on these processes, but the complexity of the system means that there is always more to learn. The study of the magnetopause is not just an academic pursuit. It has practical applications that extend to space exploration, satellite design, and even the development of new technologies. By understanding this boundary, we are better equipped to navigate the challenges of living in a spacefaring era, where our dependence on satellites and other space-based systems continues to grow. As we continue to probe the mysteries of the magnetopause, we are reminded of the intricate connections between Earth and the cosmos. This invisible boundary is a testament to the delicate balance of forces that sustain life on our planet, offering both protection and a window into the dynamic processes that shape our solar system. Each new discovery brings us one step closer to understanding not only the magnetopause itself but also the broader mechanisms that govern the universe. The magnetopause is a vivid reminder of Earth's ability to interact with and adapt to the volatile nature of the cosmos. Yet, the dynamic interactions at this boundary are only part of the larger story of Earth's relationship with the solar wind and the Sun's electromagnetic influence. The magnetopause constantly evolves, responding to solar events in ways that can be subtle or dramatic, making it a site of perpetual intrigue and investigation. To fully appreciate the magnetopause's importance, it is essential to explore its variability over time. Unlike static physical boundaries, the magnetopause expands and contracts depending on the intensity of the solar wind. During periods of low solar activity, the solar wind pressure weakens, allowing the magnetopause to expand further into space. In contrast, during intense solar storms, such as those caused by coronal mass ejections, the magnetopause can be compressed significantly, sometimes bringing it alarmingly close to Earth's surface. This dynamic nature of the magnetopause means that its effects are felt not just in the distant reaches of the magnetosphere but also in the environments closer to Earth. One significant consequence of this variability is the impact on satellites in geostationary orbits. Geostationary satellites, which orbit Earth at an altitude of approximately 36,000 kilometers, are positioned in regions that are typically well within the magnetosphere. However, during extreme solar events, the compression of the magnetopause can bring it inside this orbital distance, exposing satellites to the direct influence of the solar wind. This exposure can lead to damaging electrical discharges, communication disruptions, and even total satellite failure. Engineers must consider these potential risks when designing spacecraft, often incorporating shielding and other protective measures to ensure their resilience. The magnetopause also influences Earth's ionosphere, the electrically charged upper layer of the atmosphere. When solar wind particles breach the magnetopause, they can trigger disturbances in the ionosphere, altering its density and composition. These changes have a cascading effect on radio communication, navigation systems, and other technologies that rely on ionospheric stability. For example, during geomagnetic storms, the enhanced ionospheric currents can cause GPS signals to become unreliable, complicating everything from aviation to military operations. Another area where the magnetopause plays a critical role is in the global distribution of energy within the magnetosphere. The Earth's magnetic field lines are not static. They constantly shift and reconfigure in response to solar wind conditions. This reconfiguration is most evident during substorms, short-lived disturbances that redistribute energy from the magnetotail to other parts of the magnetosphere. The magnetopause acts as a gatekeeper during these events, regulating the entry and exit of solar wind energy and particles. Substorms are not only fascinating phenomena for scientists but also a source of awe for those lucky enough to witness their effects on the auroras. During these events, the auroras brighten and dance across the night sky, providing a tangible connection between the magnetopause's activities and the observable world. These displays serve as a reminder of the magnetosphere's dynamic nature and the interplay of forces that shape our planet's relationship with the Sun. Beyond its impact on Earth, the magnetopause provides a unique environment for studying plasma physics, the branch of science that deals with ionized gases. Plasma is the most common state of matter in the universe, yet it behaves in ways that are still not fully understood. The magnetopause, as a natural laboratory, offers invaluable insights into plasma behavior under extreme conditions. Researchers use data from satellites like NASA's Magnetospheric Multiscale (MMS) mission to study phenomena such as turbulence, wave-particle interactions, and energy transfer at the magnetopause. The MMS mission, launched in 2015, has been instrumental in advancing our understanding of the magnetopause. Comprising 4 identical spacecraft flying in a tight formation, MMS is designed to capture high-resolution measurements of magnetic and electric fields, as well as particle distributions, in the vicinity of the magnetopause. Its findings have revealed unprecedented details about magnetic reconnection, showing how this process unfolds at incredibly small scales. These discoveries not only deepen our knowledge of Earth's magnetosphere but also have broader implications for understanding similar processes occurring throughout the universe, from the Sun's corona to distant astrophysical jets. The magnetopause's study is also critical for advancing space weather prediction capabilities. As our reliance on space-based technologies grows, so does the need for accurate forecasts of geomagnetic storms and other space weather phenomena. The ability to predict how the magnetopause will respond to incoming solar wind conditions is a key component of this effort. By monitoring solar activity and modeling the interactions at the magnetopause, scientists can provide early warnings of potential disruptions, giving governments, industries, and individuals the time to prepare. While much of the focus has been on the magnetopause's protective role, it is equally important to consider its vulnerabilities. As mentioned earlier, the magnetopause is not impervious. It is a semi-permeable boundary that occasionally allows solar wind particles to penetrate. These breaches are often localized, creating what are known as flux transfer events, FTEs. During an FTE, magnetic field lines from the Sun and Earth temporarily connect, forming a conduit through which particles and energy can flow. These events are short-lived but have significant implications for the magnetosphere's overall dynamics. The study of FTEs has revealed that they occur more frequently than previously thought, suggesting that the magnetopause is a far more active and complex boundary than once believed. These discoveries challenge traditional models of the magnetosphere and highlight the need for continued research to fully understand the magnetopause's behavior. Looking ahead, the future of magnetopause research is bright, with new missions and technologies poised to provide even greater insights. For example, the European Space Agency's Solar Orbiter and NASA's Parker Solar Probe are exploring regions closer to the Sun, shedding light on the solar wind's origins and properties. By combining data from these missions with observations from Earth-based satellites, scientists hope to create a more comprehensive picture of the Sun-Earth connection. Ultimately, the magnetopause is a reminder of the intricate and ever-changing relationship between Earth and its cosmic environment. It serves as both a shield and a lens, protecting us from the Sun's most harmful effects while offering a window into the dynamic processes that govern our solar system. The more we learn about the magnetopause, the better equipped we are to navigate the challenges of living in an interconnected and space-faring world. The magnetopause is not just a protective shield, it's a critical player in Earth's space environment, constantly adapting and evolving in response to solar activity. To truly understand its significance, we must delve even deeper into the intricate processes and phenomena occurring within this dynamic boundary, and their broader implications for our planet and beyond. One particularly fascinating aspect of the magnetopause is its role as a boundary layer in the cosmic game of energy transfer. The Sun emits a continuous stream of charged particles, the solar wind, carrying not only matter but also electromagnetic energy. When these particles collide with the Earth's magnetosphere, they create a highly turbulent environment at the magnetopause. This turbulence is the result of the immense energy carried by the solar wind, which can reach speeds of 400 to 800 kilometers per second. The magnetopause, therefore, becomes a hotspot for energy dissipation, where solar wind energy is converted into other forms, such as heat and particle acceleration. The process of energy transfer at the magnetopause is governed largely by magnetic reconnection, a phenomenon that occurs when the magnetic field lines of the solar wind interact with Earth's magnetic field. Magnetic reconnection is not unique to Earth. It happens throughout the universe wherever magnetic fields converge. However, the magnetopause provides a uniquely accessible region for studying this process. During reconnection, the magnetic field lines break and rejoin in new configurations, releasing a massive amount of energy in the process. This energy release can accelerate particles to nearly the speed of light and generate powerful electromagnetic waves. Scientists have long sought to understand the precise mechanisms behind magnetic reconnection, as it holds the key to many mysteries in plasma physics. The Magnetospheric Multiscale (MMS) mission has provided unprecedented insights into this process by observing reconnection events at the smallest scales ever measured. For example, MMS has revealed that the reconnection process occurs in narrow regions called diffusion regions, where the laws of classical magnetohydrodynamics break down and the motion of particles becomes chaotic. These findings have not only advanced our understanding of Earth's magnetosphere but also provided valuable knowledge for interpreting similar processes in other astrophysical environments. Another intriguing phenomenon associated with the magnetopause is Kelvin-Helmholtz instability, K-chi. This occurs when there is a velocity shear between two fluid layers, in this case, the solar wind and the magnetosphere. At the magnetopause, this instability creates rolling, wave-like structures along the boundary. These waves can grow large enough to mix solar wind particles with those inside the magnetosphere, allowing a transfer of matter and energy. KHI waves are visually and mathematically striking, resembling rolling clouds in the sky but occurring on a cosmic scale. Their study has implications for understanding fluid dynamics not just in space but also in Earth's atmosphere and oceans. The magnetopause is also a crucial region for understanding the behavior of plasma waves, another key feature of space physics. When charged particles move through magnetic fields, they generate waves that propagate through the surrounding plasma. At the magnetopause, several types of waves are generated, including Alfvén waves, magnetosonic waves, and Whistler mode waves. These waves carry energy and information across vast distances, acting as messengers between different regions of the magnetosphere. By studying these waves, scientists can gain insights into how energy is distributed and dissipated in Earth's space environment. One of the most dramatic events linked to the magnetopause is a geomagnetic storm, a disturbance in Earth's magnetosphere caused by enhanced solar wind activity. When a coronal mass ejection (CME) from the Sun reaches Earth, it can compress the magnetopause and intensify magnetic reconnection, leading to a cascade of effects throughout the magnetosphere. These storms are not only fascinating to study but also critical to monitor, as they can have significant impacts on modern technology. During a geomagnetic storm, the energetic particles and electric currents generated in the magnetosphere can disrupt satellite operations, damage power grids, and increase radiation exposure for astronauts and high-altitude flights. One of the greatest challenges in studying the magnetopause is its extreme variability. Unlike many natural phenomena, which follow predictable cycles or patterns, the magnetopause's behavior can change rapidly and unexpectedly. This variability is driven by the highly dynamic nature of the solar wind, which can fluctuate in density, velocity, and magnetic field orientation on timescales ranging from minutes to days. These fluctuations create a constantly changing environment at the magnetopause, making it difficult to predict its behavior with high accuracy. This unpredictability has significant implications for space weather forecasting. While scientists have made great strides in monitoring solar activity and modeling the magnetosphere, there is still much to learn about how the magnetopause responds to different solar wind conditions. Improving our understanding of these interactions is a key goal of space weather research, as it would enable more accurate predictions of geomagnetic storms and other space weather events. The study of the magnetopause also has implications for planetary science and the search for extraterrestrial life. Many other planets in our solar system, including Jupiter, Saturn, and Mercury, have magnetospheres with their own magnetopauses. By comparing these magnetopauses with Earth's, scientists can gain insights into the diverse ways planets interact with the solar wind. For example, Jupiter's magnetopause is much larger than Earth's due to its stronger magnetic field, while Mercury's magnetopause is closer to the planet's surface because of its weaker field. These differences provide valuable clues about the formation and evolution of planetary magnetic fields and their role in shaping planetary environments. In the context of astrobiology, the magnetopause is particularly significant because of its role in shielding Earth from harmful solar radiation. This protection is thought to be one of the factors that made Earth hospitable to life. Studying the magnetopauses of other planets and moons can help scientists assess their potential habitability. For example, Europa, one of Jupiter's moons, has a thin atmosphere and a subsurface ocean that are influenced by Jupiter's magnetic field. Understanding how the magnetopause and other magnetic interactions affect Europa's environment could provide clues about the moon's potential to support life. The magnetopause is also a window into the broader universe, as it serves as a natural laboratory for studying fundamental plasma processes. Many of the phenomena observed at the magnetopause, such as magnetic reconnection and Kelvin-Helmholtz instability, also occur in distant astrophysical systems, from the Sun's corona to the edges of black holes. By studying these processes in the relatively accessible environment of Earth's magnetosphere, scientists can gain insights that are applicable across a wide range of astrophysical contexts. As we continue to explore the magnetopause, it becomes increasingly clear that this boundary is not just a passive shield but an active participant in Earth's space environment. Its dynamic interactions with the solar wind shape the magnetosphere, influence Earth's atmosphere, and even impact life on our planet. The magnetopause is a testament to the complex and interconnected nature of the cosmos, reminding us of the intricate balance that sustains life on Earth. The journey to understanding the magnetopause is far from over. Each new discovery reveals new questions, pushing the boundaries of our knowledge and challenging our assumptions. As technology advances and our ability to observe the cosmos improves, the magnetopause will undoubtedly continue to be a source of fascination and inspiration, offering new insights into the mysteries of the universe. The magnetopause stands as a frontier of scientific discovery, offering a continuous stream of mysteries that deepen our understanding of both our planet and the universe. Its dynamic nature makes it not just an area of interest but a keystone in unraveling fundamental cosmic processes. As we look to the future, the study of the magnetopause promises to remain a central theme in space science, with profound implications for technology, planetary protection, and even the search for extraterrestrial life. One area of ongoing research is the influence of solar wind composition on the magnetopause's behavior. The solar wind is primarily composed of electrons, protons, and alpha particles, but it can also carry trace amounts of heavier ions such as oxygen or iron. Variations in the composition of the solar wind can affect the physical and chemical processes occurring at the magnetopause. For example, heavier ions can carry more energy and momentum, potentially intensifying magnetic reconnection events. Understanding how these compositional changes impact the magnetopause can help scientists refine their models of energy transfer and plasma dynamics. Another fascinating topic is the role of the magnetopause in the generation of auroras. While the auroras are most commonly associated with the polar regions, where charged particles from the magnetosphere collide with Earth's atmosphere, their origins are intricately tied to processes at the magnetopause. During geomagnetic storms, the enhanced reconnection and particle acceleration at the magnetopause inject high-energy particles into the magnetosphere. These particles then travel along magnetic field lines toward the poles, where they interact with atmospheric gases to produce the stunning light displays we know as the northern and southern lights. By studying the magnetopause, scientists can gain a deeper understanding of the mechanisms behind auroral phenomena, leading to more accurate predictions of when and where auroras will occur. The magnetopause also serves as a natural filter for cosmic rays, high-energy particles originating from outside the solar system. While Earth's atmosphere provides an additional layer of protection, the magnetopause plays a critical role in deflecting or decelerating many of these particles before they reach the surface. The effectiveness of this shielding depends on factors such as the strength of Earth's magnetic field, the energy of the incoming cosmic rays, and the orientation of the interplanetary magnetic field. Understanding these interactions is essential for assessing the risks of cosmic ray exposure to astronauts and high-altitude flights, as well as for evaluating the potential impacts of long-term cosmic ray exposure on Earth's climate. Another dimension of magnetopause research involves its role in space weather forecasting. Space weather encompasses a range of phenomena, including geomagnetic storms, solar flares, and radiation storms, all of which can have significant impacts on human technology. For example, during a severe geomagnetic storm, the compression of the magnetopause can bring it closer to Earth's surface, exposing satellites in low Earth orbit to higher levels of radiation. This can cause disruptions in communication systems, navigation signals, and even power grids. By improving our understanding of how the magnetopause responds to different solar wind conditions, scientists can develop more reliable space weather prediction models, helping to mitigate these risks. The study of the magnetopause is not limited to Earth. As mentioned earlier, many other planets in our solar system have magnetopauses that exhibit unique characteristics. For example, Saturn's magnetopause is influenced by its extensive system of moons and rings, which add complexity to the interactions between the solar wind and the planet's magnetic field. Similarly, Uranus and Neptune have highly tilted magnetic axes and rapid rotation rates, resulting in magnetopauses that are constantly shifting and reshaping. By studying these planetary magnetopauses, scientists can gain a broader perspective on the diversity of magnetic environments in the solar system and beyond. In recent years, there has been growing interest in the magnetopauses of exoplanets, or planets outside our solar system. With the discovery of thousands of exoplanets, scientists are keen to understand how their magnetic fields and magnetopauses interact with their host stars. This research has important implications for assessing the habitability of exoplanets, as a strong magnetic field and magnetopause can protect a planet's atmosphere from being stripped away by stellar winds. For example, researchers have hypothesized that the loss of Mars's magnetic field and subsequent weakening of its magnetopause contributed to the planet's transition from a warm, wet environment to the cold, arid world we see today. By studying the magnetopauses of exoplanets, we can gain insights into their potential to support life and the long-term stability of their atmospheres. The magnetopause also has implications for our understanding of space exploration and future missions. As humanity ventures farther into space, understanding the interactions between spacecraft and planetary magnetospheres will become increasingly important. For instance, missions to the outer planets, or their moons, must account for the dynamic behavior of magnetopauses and the radiation environments they create. By studying the magnetopause, scientists can develop better shielding technologies and navigation strategies, ensuring the safety and success of these missions. In addition to its scientific and practical significance, the magnetopause offers a sense of wonder and inspiration. It represents a boundary not just in physical space but also in human understanding, challenging us to push the limits of what we know about the universe. The dynamic interactions at the magnetopause are a reminder of the intricate and interconnected nature of cosmic systems, where even seemingly small changes can have far-reaching effects. As we continue to explore the magnetopause, new technologies and missions will play a crucial role in advancing our knowledge. For example, the upcoming European Space Agency's Solar Orbiter mission is designed to study the Sun's influence on the solar wind and its interactions with planetary magnetospheres. By providing high-resolution observations of the Sun's activity, Solar Orbiter will help scientists better understand the forces driving the solar wind and its impact on the magnetopause. Meanwhile, advancements in computational modeling and simulation are enabling researchers to create more accurate and detailed representations of the magnetopause and its interactions with the solar wind. These models can simulate the behavior of individual particles and magnetic field lines, providing insights into processes that are difficult or impossible to observe directly. By combining observations from spacecraft with these sophisticated models, scientists can piece together a more complete picture of the magnetopause and its role in Earth's space environment. The magnetopause is not just a shield or a boundary. It is a dynamic, living system that reflects the complex interplay of forces shaping our planet and the universe. Its study is a testament to the power of human curiosity and the endless possibilities of scientific discovery. As we look to the future, the magnetopause will undoubtedly remain a source of fascination and inspiration, offering new insights into the mysteries of the cosmos and our place within it. The magnetopause remains an ever-evolving frontier, captivating scientists and sparking imaginations. As research deepens, new mysteries emerge, compelling humanity to explore this dynamic boundary that serves as Earth's first line of defense against the vast, untamed forces of space. One of the most fascinating aspects of the magnetopause is its role in magnetic reconnection. This process is not only fundamental to the behavior of Earth's magnetosphere but is also a universal phenomenon occurring across the cosmos, from solar flares on the Sun to the magnetic fields of distant stars and galaxies. Magnetic reconnection at the magnetopause involves the breaking and reconnecting of magnetic field lines, which releases immense amounts of energy. This energy fuels geomagnetic storms, accelerates particles to near-light speeds, and creates stunning auroras in Earth's skies. Understanding magnetic reconnection at the magnetopause is crucial for predicting and mitigating the effects of space weather. During periods of intense solar activity, such as coronal mass ejections (CMEs), the solar wind's magnetic field can align in such a way that it enhances reconnection at the magnetopause. This alignment, known as a southward interplanetary magnetic field (IMF), allows for a stronger connection between the solar wind and Earth's magnetic field, leading to increased energy transfer. The result can be powerful geomagnetic storms capable of disrupting power grids, disabling satellites, and endangering astronauts in space. To study this, scientists rely on cutting-edge spacecraft such as NASA's Magnetospheric Multi-Scale (MMS) mission, which was specifically designed to investigate magnetic reconnection in unprecedented detail. The MMS mission uses four identical spacecraft flying in a tight formation to measure the microphysics of reconnection at the magnetopause. By capturing data on the behavior of particles and fields at the smallest scales, MMS has provided groundbreaking insights into how magnetic reconnection occurs and how it influences the magnetosphere. Another area of interest is how the magnetopause interacts with Earth's plasmasphere, a region of cold, dense plasma that surrounds the planet. The plasmasphere is fed by particles from Earth's ionosphere, which are trapped and rotated by the planet's magnetic field. During periods of heightened solar activity, the plasmasphere can extend outward and interact with the magnetopause. These interactions can lead to the formation of structures such as plasmaspheric plumes, which play a role in energy transfer between the magnetosphere and the solar wind. The behavior of the magnetopause is also influenced by dynamic pressure from the solar wind. This pressure is not constant but varies depending on solar activity, the density and speed of the solar wind, and other factors. When the solar wind pressure increases, the magnetopause is compressed, moving closer to Earth. Conversely, during periods of low solar wind pressure, the magnetopause can expand outward. This constant fluctuation makes the magnetopause a highly dynamic boundary, capable of responding to changes in the space environment almost instantaneously. Interestingly, the location and shape of the magnetopause are not uniform. It is highly asymmetrical, with the day side, facing the Sun, being much closer to Earth than the night side. The night side extends into a long, tail-like structure called the magnetotail, which stretches millions of kilometers into space. This asymmetry is due to the constant pressure of the solar wind on the day side and the stretching effect on the night side as Earth's magnetic field lines are pulled away. The magnetotail itself is a region of immense scientific interest, as it is the site of many dynamic processes, including the acceleration of particles that eventually create auroras. One of the least understood phenomena associated with the magnetopause is the Kelvin-Helmholtz instability, K-chi. This occurs when there is a velocity shear between two fluids, in this case, the solar wind and the magnetospheric plasma. At the magnetopause, K-chi can generate waves and vortices that mix the plasmas from the two regions. These vortices can enhance particle transport and energy transfer across the magnetopause, making them a critical area of study for understanding how the magnetosphere interacts with the solar wind. The magnetopause also has a profound impact on Earth's radiation belts, also known as the Van Allen belts. These are zones of charged particles trapped by Earth's magnetic field, and their behavior is influenced by processes occurring at the magnetopause. For example, during magnetic reconnection events or geomagnetic storms, particles from the solar wind can be injected into the radiation belts, increasing their intensity. Conversely, the magnetopause can act as a boundary that prevents particles from escaping the radiation belts into space. Understanding these interactions is vital for protecting satellites and other space-based technologies. In the realm of comparative planetology, studying Earth's magnetopause provides a valuable framework for understanding other planets and celestial bodies. For instance, Jupiter's magnetosphere is the largest in the solar system, and its magnetopause is shaped not only by the solar wind but also by the intense plasma output from its volcanic moon, Io. Similarly, Mercury, with its weak magnetic field and close proximity to the Sun, has a magnetopause that is much smaller and more compressed than Earth's. By comparing these different magnetopauses, scientists can uncover the fundamental principles governing magnetic fields and their interactions with the solar wind. The magnetopause is also a key player in the search for extraterrestrial life. A strong magnetosphere and a well-defined magnetopause are thought to be essential for protecting a planet's atmosphere from being eroded by stellar winds. For example, Mars, which has a weak magnetic field, has lost much of its atmosphere over time due to the lack of a protective magnetopause. In contrast, Earth's magnetopause has preserved our atmosphere, creating a stable environment for life to thrive. By studying the magnetopauses of exoplanets, scientists hope to identify potentially habitable worlds that possess similar protective barriers. In the future, advancements in technology and space exploration will continue to enhance our understanding of the magnetopause. Missions like the European Space Agency's Solar Orbiter and NASA's Parker Solar Probe are already providing valuable data on the Sun and its influence on the solar wind. These observations will help scientists refine their models of the magnetopause and its interactions with the Sun. As humanity looks to establish a permanent presence in space, the magnetopause will remain a critical area of study. Understanding its behavior will be essential for designing spacecraft and habitats capable of withstanding the harsh conditions of the space environment. It will also play a role in planning missions to other planets and moons, where the presence or absence of a magnetopause could influence the safety and success of these endeavors. The magnetopause is not just a boundary, it is a gateway to understanding the complex and interconnected systems that shape our universe. Its study has far-reaching implications, from protecting our technology and infrastructure to uncovering the secrets of distant planets and the conditions for life. As we continue to explore this dynamic region, the magnetopause will undoubtedly remain at the forefront of space science, inspiring new discoveries and expanding our knowledge of the cosmos. The magnetopause is a vivid reminder of the ever-changing nature of the universe. Despite its protective role, it is not a static shield. It is a dynamic interface, continually shaped and reshaped by the solar wind's variability and the Earth's magnetic activity. Every fluctuation in solar wind pressure, every coronal mass ejection, and every twist of the interplanetary magnetic field leaves an imprint on the magnetopause, altering its structure and behavior in real time. This variability means that the magnetopause is not just a passive boundary but an active participant in the space weather system. It serves as a sentinel, responding to external forces while simultaneously influencing the internal dynamics of Earth's magnetosphere. The interplay of forces at the magnetopause has profound implications not only for Earth but also for understanding the broader cosmic environment. A striking example of the magnetopause's dynamic behavior occurs during geomagnetic substorms. These are brief, intense disturbances in Earth's magnetosphere, often triggered by interactions at the magnetopause. When magnetic reconnection happens on the dayside magnetopause, it sets off a cascade of energy transfer processes that ripple through the magnetosphere. These effects are most visible in the auroral regions, where vibrant displays of light dance across the night sky, fueled by charged particles accelerated by the magnetopause's interactions. Another critical aspect of the magnetopause is its role in particle acceleration. During reconnection events or high-energy solar wind interactions, particles from both the solar wind and Earth's magnetosphere can be accelerated to extremely high speeds. These accelerated particles contribute to the radiation belts and can pose significant risks to spacecraft and astronauts. Understanding how and why these particles are accelerated at the magnetopause is essential for mitigating their potentially harmful effects. The magnetopause also acts as a boundary between two very different plasmas: the hot, tenuous solar wind plasma and the cooler, denser plasma of Earth's magnetosphere. This contrast creates a fascinating environment for plasma physics research. At the magnetopause, scientists can study phenomena such as wave-particle interactions, plasma instabilities, and energy transfer mechanisms in a way that is not possible in laboratory settings on Earth. The insights gained here have applications far beyond our planet, helping us understand similar processes in other astrophysical systems. In addition to its scientific significance, the magnetopause has practical importance for space exploration and technology. Satellites in geostationary orbit, which are crucial for communication, weather monitoring, and navigation, often operate near the boundary of the magnetosphere. Changes in the location or behavior of the magnetopause can expose these satellites to increased radiation, potentially damaging their systems or shortening their operational lifespans. Accurate models of the magnetopause are therefore vital for satellite operators and mission planners. The magnetopause's influence extends to Earth's ionosphere, the layer of the atmosphere that interacts with space. When energy and particles from the solar wind cross the magnetopause, they can trigger disturbances in the ionosphere, affecting radio communications and GPS signals. Understanding the coupling between the magnetosphere and ionosphere is a key focus of space weather research, with the magnetopause playing a central role in this connection. From an educational perspective, the magnetopause is an excellent example of the interdisciplinary nature of space science. Its study requires expertise in fields ranging from plasma physics and magnetohydrodynamics to astrophysics and planetary science. The magnetopause also provides a tangible link between abstract scientific concepts and real-world phenomena, making it an ideal topic for engaging students and the public in the wonders of space. Looking to the future, the study of the magnetopause will benefit from emerging technologies and international collaborations. Advanced spacecraft equipped with high-resolution instruments will allow scientists to probe the magnetopause at smaller scales and in greater detail than ever before. Ground-based observatories, supercomputers, and artificial intelligence will complement these efforts, enabling researchers to simulate the magnetopause's behavior and predict its responses to solar events with unprecedented accuracy. Beyond Earth, the study of the magnetopause has implications for planetary exploration. Understanding the magnetopause's role in protecting Earth's atmosphere and surface from the solar wind can inform efforts to study other planets, particularly those with weak or non-existent magnetic fields. For example, missions to Mars and Venus have revealed the consequences of atmospheric erosion caused by the lack of a strong magnetopause. These findings highlight the importance of magnetic fields and their boundaries in shaping the habitability of planets. The magnetopause also serves as a natural laboratory for studying universal processes. Magnetic reconnection, particle acceleration, and wave-particle interactions are not unique to Earth. They occur throughout the universe in systems as diverse as the Sun's corona, supernova remnants, and active galactic nuclei. By studying these processes at the magnetopause, scientists can gain insights into phenomena that are otherwise inaccessible due to distance or scale. As humanity continues to venture into space, the magnetopause will remain a critical focus of research. It represents both a challenge and an opportunity, a boundary to be understood and a gateway to new discoveries. By unraveling its mysteries, scientists can not only protect our planet and our technology, but also deepen our understanding of the forces that shape the cosmos. The magnetopause is a testament to the interconnectedness of the universe. It reminds us that Earth is not isolated but is part of a vast, dynamic system influenced by the Sun and the broader galaxy. As we continue to explore this fascinating boundary, we are not just learning about the magnetopause itself. We are uncovering the fundamental principles that govern our place in the universe. The magnetopause, with its intricate dance between Earth's magnetic field and the solar wind, offers more than just a boundary. It is a symbol of the delicate balance that sustains life on our planet, acting as both protector and a subject of intense scientific study. This interplay can sometimes feel like a cosmic game of tug-of-war, where the forces of the solar wind push and pull against Earth's defenses. But this balance is not always easy to maintain. The solar wind, originating from the Sun, is not a constant stream. It varies in intensity, speed, and density, influenced by the Sun's activity. During periods of solar calm, the wind is relatively gentle, allowing the magnetopause to maintain a stable position well beyond Earth's atmosphere. However, during solar storms, such as those caused by coronal mass ejections, CMEs, the intensity of the solar wind can increase dramatically. This causes the magnetopause to contract, sometimes bringing it dangerously close to Earth. The result can be a cascade of events within the magnetosphere that affects everything from satellite orbits to the auroras at the poles. CMEs are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. These eruptions carry with them immense amounts of energy and charged particles, traveling at speeds upwards of 1,000 kilometers per second. When these particles collide with the magnetopause, the resulting shockwaves can ripple through the entire magnetosphere, causing geomagnetic storms. These storms can produce beautiful auroras but can also lead to significant disruptions in communications and satellite operations. The magnetopause's reaction to solar storms is an area of active research. Scientists study how the magnetopause reshapes itself in response to these events, hoping to predict its behavior more accurately. As we expand our understanding of this boundary, it is becoming clearer how the magnetopause's dynamics influence space weather patterns and how these patterns can, in turn, affect life on Earth. Satellites that orbit Earth in the outer regions of the magnetosphere are often the first to experience these storms. Understanding the interactions at the magnetopause allows engineers to design better spacecraft that can withstand the harsh effects of space weather. One of the most exciting aspects of the magnetopause is its potential to teach us about the broader cosmos. The interactions between the solar wind and Earth's magnetic field are not unique to our planet. Many other planets, moons, and celestial bodies in the solar system and beyond are subject to similar forces. For example, Jupiter, with its massive magnetic field, has a magnetopause that is far more massive and energetic than Earth's. Studying these planetary magnetospheres and their magnetopauses can reveal a great deal about the environments of distant planets, moons, and even exoplanets. Mars, for instance, presents a stark contrast to Earth in terms of magnetopause and solar wind interaction. The red planet once had a magnetic field, but it disappeared billions of years ago. Without a magnetopause to protect it, the Martian atmosphere was stripped away by the relentless solar wind, a process that likely contributed to the planet's transition from a potentially habitable world to the dry, barren desert we see today. This loss of atmosphere has profound implications for the search for life on Mars and for understanding the role that magnetospheres play in preserving planetary habitability. In contrast, Venus, which also lacks a global magnetic field, experiences a unique interaction with the solar wind. Instead of a magnetopause, Venus has what is called an ionosphere that interacts directly with the solar wind. This direct contact leads to an even more extreme form of atmospheric stripping, one that scientists believe may have played a significant role in Venus' transformation into the harsh, high-pressure world we know today. Understanding the magnetopause on Earth also sheds light on the dynamics of distant stellar and galactic phenomena. Magnetic fields and solar winds are common in the universe, and the principles that govern the interaction between a star's solar wind and a planet's magnetic field can apply to stars, black holes, and other cosmic structures. The study of magnetospheres and magnetopauses, particularly those around massive stars or black holes, can help us understand the vast and energetic space weather that shapes galaxies and star systems. For example, the magnetospheres of neutron stars and pulsars are some of the most extreme and powerful in the universe. These objects, which are the remnants of massive stars that have exploded in supernovae, have magnetic fields so strong they can affect entire planets. While the magnetopause around these objects may be beyond our immediate reach, studying their properties can yield valuable insights into the forces at play around our own planet's magnetopause. Similarly, when considering the vastness of the universe, the study of the magnetopause on a planetary scale can help us understand how cosmic winds shape the environments of distant exoplanets. Some exoplanets orbit stars with intense stellar winds, much stronger than the solar wind. The nature of these winds, the magnetospheres that protect these planets, and the interactions between the two, could be crucial factors in determining whether life can exist on these far-off worlds. Back here on Earth, the magnetopause continues to challenge our understanding of space weather and its impact on our technological systems. With humanity's increasing reliance on satellites for communication, navigation, and weather prediction, understanding the behavior of the magnetopause is no longer just a matter of scientific curiosity but one of practical necessity. As the magnetopause shifts, it can create varying levels of radiation exposure for these satellites, which can damage delicate electronics and disrupt services. This is why predicting and monitoring space weather events that involve the magnetopause is a priority for space agencies and private companies alike. In addition to satellites, the magnetopause's role in protecting Earth's atmosphere from solar winds also has a profound effect on the habitability of Earth itself. The shield created by the magnetopause prevents the solar wind from stripping away our atmosphere, which is crucial for maintaining life as we know it. Without this protection, Earth's atmosphere would gradually erode, potentially leading to the kind of environmental collapse seen on planets like Mars and Venus. This delicate balance is a constant reminder that the forces of nature, while awe-inspiring and protective, are also highly fragile. The Sun's activity can change the structure of our magnetosphere, and even small fluctuations in solar wind can trigger ripple effects that reach all the way to the Earth's surface. This is why the study of the magnetopause and its interactions with the solar wind is essential for understanding the fundamental processes that govern space weather and its influence on the planet. To fully comprehend the magnetopause's role, we must also explore its relationship with Earth's ionosphere and its impact on radio communications. The ionosphere, which is made up of electrically charged particles, plays a crucial role in reflecting radio waves back to Earth, enabling communication over long distances. However, disturbances in the magnetosphere, particularly those occurring at the magnetopause, can create irregularities in the ionosphere, leading to issues with radio signal quality and GPS accuracy. This is especially true during solar storms, which can cause sudden ionospheric disturbances, SIDS, that disrupt these signals, making it harder to rely on global navigation systems. By studying the magnetopause, scientists are not only learning more about space weather and its effects on technology, but they are also unlocking deeper mysteries about the universe. The magnetopause acts as a window into the interactions between the solar wind and planetary environments, and by understanding these forces, we can better predict the behavior of distant planetary systems, stars, and galaxies. As we move forward into the future of space exploration, understanding the magnetopause and its complex interactions will be crucial. Whether it is protecting astronauts on a journey to Mars, ensuring the safety of satellites, or safeguarding our planet's atmosphere, the role of this boundary cannot be overstated. Its study offers a glimpse into the universe's fundamental workings and underscores the importance of understanding the delicate balance between celestial forces. The magnetopause is more than just a boundary. It is a dynamic, living phenomenon that constantly interacts with the environment around it. It is a shield that protects us, a gatekeeper to space, and a subject of endless fascination and discovery. Through continued research and exploration, we will uncover even more about the forces that shape the magnetopause and, in turn, our understanding of the universe itself. As we continue to probe deeper into the complexities of the magnetopause and its role in protecting our planet, it's important to look at the technological advancements that allow scientists to study this boundary in such detail. The magnetopause is not something we can easily observe with the naked eye, and thus, we rely on a variety of space-based tools and missions to gather data about this cosmic phenomenon. One of the most significant contributors to our understanding of the magnetopause is the NASA's Magnetospheric Multiscale Mission, MMS, launched in 2015. The MMS mission consists of 4 identical spacecraft that work together in a coordinated manner to study the magnetosphere in unprecedented detail. These spacecraft are designed to fly in a precise formation, allowing them to collect data from various points in the magnetosphere and magnetopause, particularly during intense solar wind events like geomagnetic storms. The MMS is equipped with cutting-edge instruments that measure the electric and magnetic fields, as well as the density and velocity of particles in space. By gathering these measurements from multiple spacecraft in different parts of the magnetosphere, the MMS provides a comprehensive picture of how the solar wind interacts with the Earth's magnetic field, how the magnetopause behaves under stress, and how energy is transferred through the system. This mission has opened up new avenues for studying space weather and offers an unprecedented look at the dynamics of the magnetosphere and magnetopause. Another critical part of our research into the magnetopause comes from the European Space Agency's ESA cluster mission. This mission, launched in 2000, consists of 4 spacecraft that also work in tandem to study the Earth's magnetosphere and its interactions with the solar wind. The cluster mission focuses on providing data that enhances our understanding of how the magnetopause reacts to varying solar wind conditions, and how the solar wind's energy is transferred into the Earth's magnetosphere. What makes the cluster mission particularly valuable is its ability to measure phenomena such as magnetic reconnection. This is the process by which the magnetic field lines in the magnetopause break and reconnect in a different configuration. Magnetic reconnection is a fundamental mechanism through which energy is transferred from the solar wind into the Earth's magnetosphere, and it plays a crucial role in the dynamics of the magnetopause. The cluster spacecraft provide invaluable data on this process, helping scientists understand how energy builds up in the magnetosphere and leads to events like geomagnetic storms and auroras. Beyond dedicated space missions, there are also ground-based observatories and observatories in low Earth orbit that play an essential role in monitoring space weather. Instruments like magnetometers and ionosons are crucial for understanding the behavior of the magnetosphere and magnetopause. These ground-based observatories measure the strength and direction of the Earth's magnetic field, helping scientists track changes in the magnetosphere and predict when the magnetopause might experience stress from an incoming solar storm. As we continue to collect more data from these missions and ground-based observatories, we are starting to develop more accurate models of the magnetopause and its behavior. This is a crucial step in improving our ability to predict space weather events, which is of increasing importance as we become more reliant on technology that is vulnerable to space weather disruptions. Solar storms, which originate from disturbances in the Sun's magnetic field, are one of the most significant threats to our modern technological infrastructure. The solar wind carries these disturbances, and when the solar wind encounters the magnetopause, the boundary can become unstable, causing geomagnetic storms. These storms can have wide-ranging effects on Earth, from disrupting satellite communications and navigation systems to damaging power grids. In extreme cases, solar storms have the potential to cause widespread blackouts, which could have devastating consequences for society. The 1859 Carrington event is one of the most famous examples of a powerful solar storm that impacted Earth. This event, which is named after British astronomer Richard Carrington, produced a massive solar flare and coronal mass ejection that struck Earth. The result was an intense geomagnetic storm that caused telegraph systems to fail, and auroras were visible as far south as the Caribbean. If such an event were to occur today, it could cause widespread disruptions to communication systems, satellite networks, and power grids, potentially leading to a global crisis. Understanding the magnetopause's response to solar wind and solar storms is critical to developing strategies for mitigating the effects of space weather. Scientists are working on methods to predict when solar storms are likely to occur, based on the behavior of the Sun. They are also investigating ways to protect our technological infrastructure by designing spacecraft and satellites that are more resilient to space weather and by developing systems to shield power grids from the effects of geomagnetic storms. In addition to protecting technology, understanding the magnetopause is also crucial for space exploration. As humanity looks to venture further into space, particularly with the goal of sending astronauts to Mars, we must consider the challenges posed by space weather. The radiation and solar wind encountered beyond Earth's magnetosphere present a significant threat to astronauts. The magnetosphere acts as a shield, but once we leave its protective embrace, we are exposed to the harsh conditions of deep space. This is why understanding the magnetopause's dynamics is essential for planning long-duration space missions and ensuring the safety of astronauts. Scientists are working on developing advanced shielding technologies to protect spacecraft and astronauts from the dangers of solar radiation and solar wind. One promising area of research involves creating artificial magnetic fields that could replicate the protective effects of the Earth's magnetosphere. This could potentially shield astronauts on missions to Mars or beyond from harmful radiation and provide a safe environment for long-term habitation. In addition, understanding the magnetopause can help us understand the broader processes that govern planetary habitability. As we continue to search for exoplanets in the habitable zone of distant stars, we must consider the role of planetary magnetic fields and magnetopauses in protecting potential life forms from the harmful effects of stellar radiation. Planets that lack a strong magnetic field, like Mars, may be more susceptible to atmospheric stripping by solar wind, making it more difficult for life to thrive. By studying the magnetopause on Earth and other planets in our solar system, we can gain insights into the factors that make a planet habitable. As our understanding of the magnetopause evolves, so too will our ability to predict and mitigate the effects of space weather on Earth. The more we learn about this dynamic boundary, the better equipped we will be to protect our technology, our infrastructure, and even ourselves from the unpredictable forces of the solar wind. And as we look to the stars, the magnetopause will continue to be a key player in our quest to explore the cosmos. The magnetopause is not just an invisible barrier that shields our planet from the solar wind, it is a fascinating, dynamic region that holds the key to understanding space weather, planetary protection, and even the future of space exploration. Its study connects the forces that govern our planet with the broader processes that shape the universe, and as we continue to explore its mysteries, we uncover deeper insights into the fundamental nature of space and the universe. The magnetopause is not simply a scientific curiosity, it is the silent guardian of our planet, shielding us from the vast, untamed energy of space. And in this role, it is vital to the survival of life on Earth, as well as to the future of humanity, as we venture into the depths of the cosmos. The magnetopause is more than a static boundary, it is an active, constantly shifting frontier between the forces of the Sun and the resilience of our planet. To truly understand its significance, we must dive deeper into its intricate behavior during different solar events and the consequences that ripple through Earth's systems. One of the most dynamic processes occurring at the magnetopause is magnetic reconnection. This phenomenon is akin to an intricate cosmic dance, where magnetic field lines from the Sun and Earth converge, break apart, and reconnect in new configurations. During this process, immense amounts of energy are released, allowing charged particles from the solar wind to penetrate the Earth's magnetosphere. This interaction is not random but highly influenced by the orientation of the interplanetary magnetic field, IMF, a component of the solar wind. When the IMF is southward, opposite to the Earth's northward magnetic field at the magnetopause, conditions are ripe for reconnection. This alignment creates open, magnetic field lines that allow solar wind particles to enter the magnetosphere, leading to a cascade of effects. These include the intensification of the auroras and geomagnetic storms, which can disrupt communication systems, satellites, and even ground-based electrical grids. The auroras, or the northern and southern lights, are among the most visible manifestations of magnetopause activity. When solar wind particles breach the magnetosphere, they travel along Earth's magnetic field lines toward the polar regions. There, they collide with molecules in the upper atmosphere, such as oxygen and nitrogen, causing these particles to emit light. The result is a breathtaking display of shimmering greens, reds, purples, and blues. However, the beauty of the auroras belies the potentially disruptive power of the processes that create them. During geomagnetic storms, the energy transferred from the solar wind into Earth's magnetosphere can become overwhelming. The magnetopause, normally positioned at a distance of approximately 10 Earth radii from our planet, can be compressed closer to Earth by the pressure of a strong solar wind. This compression not only intensifies magnetic reconnection but also impacts satellites in geostationary orbits, exposing them to charged particles that can damage their electronics and disrupt their functionality. One notable example of such an event occurred during the 1989 geomagnetic storm, which caused a massive blackout in Quebec, Canada. The solar wind's interaction with the magnetopause during this storm induced electric currents and power lines on the ground, overwhelming transformers and leading to widespread power outages. This serves as a stark reminder of the interconnectedness of the magnetopause and human technology, emphasizing the importance of continued research and preparedness. In addition to geomagnetic storms, the magnetopause plays a critical role in shielding Earth from coronal mass ejections, CMEs. These are massive bursts of solar plasma and magnetic fields that are ejected from the Sun's corona during solar flares. When a CME is directed toward Earth, it can carry billions of tons of charged particles traveling at speeds of up to 3,000 kilometers per second. The magnetopause acts as the first line of defense, absorbing and deflecting much of this energy. However, a particularly strong CME can compress the magnetopause significantly, allowing a greater influx of solar wind particles and leading to severe space weather events. Understanding the magnetopause's response to CMEs is crucial not only for protecting technology, but also for safeguarding human health during space missions. Astronauts beyond the Earth's protective magnetosphere are directly exposed to the intense radiation from solar storms and CMEs. As we plan for future missions to the Moon, Mars, and beyond, developing advanced shielding technologies and accurate space weather forecasting systems will be essential for ensuring the safety of astronauts. Beyond Earth, the study of the magnetopause extends to other planets in our solar system. Each planet with a magnetic field has its own magnetopause, shaped by the interplay between the planet's magnetic field and the solar wind. For example, Jupiter's magnetopause is immense, extending millions of kilometers from the planet due to its incredibly strong magnetic field. In contrast, Mars, which lacks a global magnetic field, has localized magnetic bubbles that provide limited protection from the solar wind. These differences highlight the critical role of magnetopauses in determining a planet's ability to sustain an atmosphere and, by extension, its habitability. The comparative study of magnetopauses across the solar system also provides insights into the history of planetary evolution. Mars, for instance, is thought to have once had a global magnetic field similar to Earth's. Over time, however, its magnetic field weakened, allowing the solar wind to strip away much of its atmosphere. Today, the thin Martian atmosphere offers little protection from radiation, posing a significant challenge for future human exploration and potential colonization. In contrast, Earth's magnetopause has proven to be a robust and adaptive shield, capable of withstanding even the most intense solar events. This resilience is a testament to the intricate balance of forces that govern our planet's magnetic field and its interaction with the solar wind. However, as we continue to study the magnetopause, we must also consider the potential long-term effects of changes in Earth's magnetic field. Earth's magnetic field is not static. It undergoes periodic reversals, where the magnetic north and south poles switch places. These reversals occur roughly every 200,000 to 300,000 years, although the timing is irregular. During a reversal, the strength of the magnetic field decreases, potentially weakening the magnetopause and increasing Earth's exposure to solar wind particles. While the last reversal occurred about 780,000 years ago, the magnetic field has been weakening over the past century, leading some scientists to speculate that a reversal may be underway. The implications of a magnetic field reversal for the magnetopause and space weather are not fully understood, but they could include increased radiation exposure and more frequent geomagnetic storms. Studying the magnetopause during such transitions will be critical for predicting and mitigating potential impacts on Earth's environment and technology. As we unravel the mysteries of the magnetopause, we also open the door to a deeper understanding of the universe. The processes that govern the magnetopause, such as magnetic reconnection and plasma dynamics, are not unique to Earth. They occur throughout the cosmos, from the magnetospheres of other planets to the environments around stars and black holes. By studying the magnetopause, we gain insights into the fundamental forces that shape the universe and our place within it. In many ways, the magnetopause serves as a microcosm of the broader cosmic interactions that define our existence. It is a dynamic boundary where opposing forces collide, creating both challenges and opportunities for exploration and discovery. As we continue to study this fascinating region, we not only deepen our understanding of Earth and its relationship with the Sun but also contribute to the ongoing quest to explore the unknown. The magnetopause is a reminder of the delicate balance that sustains life on Earth, shielding us from the Sun's relentless energy while allowing just enough to support life. It is a testament to the intricate interplay of forces that govern our planet and a symbol of the resilience and adaptability of the natural world. And as we look to the stars, the magnetopause will continue to inspire awe and curiosity, guiding us on our journey to uncover the mysteries of the universe. The magnetopause is not just a boundary but a window into the dynamic relationship between our planet and the Sun. To appreciate its complexity, it's essential to delve further into the phenomena it governs, its role in Earth's magnetosphere, and its implications for technology, exploration, and understanding of other celestial bodies. One of the most fascinating aspects of the magnetopause is its constantly shifting nature. The Sun, as a G-type main-sequence star, exhibits cycles of activity that peak approximately every 11 years. During periods of high solar activity, known as solar maximum, the Sun produces more intense solar wind and frequent coronal mass ejections, CMEs. This heightened activity compresses the magnetopause closer to Earth, intensifying its interactions with the solar wind. During these periods, we often observe dramatic space weather events. For instance, intense geomagnetic storms triggered by CME impacts can disrupt power grids, damage satellites, and interfere with radio communications. The magnetopause, though a protective barrier, becomes a region of vulnerability under such extreme conditions. Scientists and engineers are continually working on predictive models to anticipate the effects of these solar events, which can provide crucial lead time for mitigating their impact on Earth's infrastructure. Satellites, particularly those in geostationary orbits, operate near the outer edge of the magnetosphere, making them susceptible to changes in the magnetopause. These satellites are vital for communication, navigation, weather forecasting, and scientific research. When the magnetopause compresses during a solar storm, these satellites can be exposed to increased radiation levels, potentially causing malfunctions or permanent damage. To counter this, satellite operators often put satellites into a protective mode when a solar storm is predicted, minimizing the risk of harm. In addition to its practical implications, the magnetopause provides a natural laboratory for studying fundamental physical processes. Magnetic reconnection, for example, is not just a phenomenon observed at the magnetopause but a universal process occurring throughout the cosmos. In the Sun's corona, reconnection powers solar flares, releasing energy equivalent to billions of nuclear bombs in a matter of minutes. In distant galaxies, similar processes occur near black holes and neutron stars, driving jets of plasma that extend for thousands of light years. By studying magnetic reconnection at the magnetopause, scientists gain insights that can be applied to these distant astrophysical phenomena. This research also has practical applications closer to home, such as in the development of nuclear fusion technology. Magnetic confinement fusion, a potential source of nearly limitless clean energy, relies on controlling plasma with magnetic fields. Understanding reconnection at the magnetopause helps refine these techniques, bringing us closer to realizing the dream of fusion power. Beyond Earth's immediate environment, the concept of the magnetopause is pivotal in understanding other planets. Jupiter's magnetosphere, for instance, is the largest structure in the solar system, extending far beyond the planet itself. The Jovian magnetopause, shaped by the interaction of Jupiter's powerful magnetic field with the solar wind, exhibits many of the same processes as Earth's but on a much grander scale. Studying these similarities and differences enhances our understanding of magnetospheric dynamics and their role in planetary protection. Venus, on the other hand, offers a stark contrast. Lacking a significant magnetic field, it does not have a magnetopause. Instead, the solar wind interacts directly with Venus's upper atmosphere, stripping away particles over time. This process, known as atmospheric escape, has likely contributed to the planet's transformation from a potentially habitable world to the inhospitable furnace it is today. Comparing Venus with Earth highlights the critical role of a magnetic field and magnetopause in preserving a planet's atmosphere and, by extension, its habitability. Mars provides another intriguing case study. While it lacks a global magnetic field, Mars has localized magnetic fields in its crust, creating small magnetopause-like structures known as mini-magnetospheres. These localized regions provide limited protection from the solar wind, offering a glimpse into what Earth might experience during periods of magnetic field weakening or reversal. Understanding how these mini-magnetospheres interact with the solar wind helps scientists piece together the history of Mars's atmosphere and its potential for hosting life in the past. The magnetopause is also a key factor in shaping the environments of exoplanets, planets outside our solar system. As scientists discover more exoplanets, understanding their magnetospheres becomes crucial for assessing their habitability. A strong magnetosphere and magnetopause can shield an exoplanet from stellar wind, protecting its atmosphere and surface conditions. Conversely, a weak or non-existent magnetosphere could leave an exoplanet exposed to harmful radiation, reducing its chances of supporting life. To explore these phenomena further, space agencies around the world have launched numerous missions. NASA's Magnetospheric Multiscale (MMS) mission, for instance, is dedicated to studying magnetic reconnection, particle acceleration, and turbulence in Earth's magnetosphere. By flying 4 spacecraft in close formation through the magnetopause, MMS captures high-resolution data on its structure and behavior. These insights not only deepen our understanding of Earth's magnetosphere but also contribute to broader astrophysical knowledge. Meanwhile, the European Space Agency's Cluster mission and Japan's G-Tail mission have provided complementary perspectives on the magnetopause, offering a global view of its dynamics. Together, these missions paint a detailed picture of the magnetopause as a dynamic, complex, and ever-changing boundary that plays a critical role in Earth's interaction with the Sun. As we look to the future, the study of the magnetopause will continue to be a cornerstone of space science. With the increasing reliance on space-based technologies and the growing interest in human exploration of the Moon, Mars, and beyond, understanding the magnetopause is more important than ever. It not only protects our planet from the Sun's volatile energy but also serves as a gateway to the cosmos, where the same principles that govern its behavior can be observed on a universal scale. The magnetopause, in all its complexity, reminds us of the delicate balance that sustains life on Earth. It is a region of constant interaction and transformation, where the forces of the Sun meet the resilience of our planet. By studying this boundary, we not only safeguard our technology and future space missions but also unlock the secrets of the universe, one discovery at a time. The magnetopause, often described as the outermost frontier of Earth's magnetic defense system, is a constant reminder of the delicate interplay between celestial forces. It is the invisible shield that ensures life as we know it can thrive, shielding our planet from harmful solar and cosmic radiation. Yet, its behavior is anything but static. It is an ever-changing boundary, shaped by the unpredictable rhythms of the Sun and the intricate workings of Earth's own magnetic field. One of the most intriguing phenomena associated with the magnetopause is the generation of auroras. When charged particles from the solar wind penetrate the magnetosphere, often through magnetic reconnection at the magnetopause, they are funneled towards the polar regions by Earth's magnetic field. As these particles collide with molecules in the upper atmosphere, they excite the atoms, causing them to emit light. This natural light show, known as the aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere, is a direct result of the dynamic processes occurring at the magnetopause. Auroras are not just visually stunning, they are also a scientific goldmine. By studying the frequency, intensity, and location of auroras, scientists can infer the behavior of the magnetopause and the solar wind conditions that influence it. For instance, during periods of high solar activity, auroras can be seen much closer to the equator, indicating a significant compression of the magnetosphere. Conversely, during periods of low solar activity, the magnetopause extends farther from Earth, and auroras retreat to higher latitudes. The magnetopause is also a critical player in what scientists call the space weather system. Space weather refers to the conditions in the space environment surrounding Earth, influenced by the Sun's activity. Severe space weather events, such as geomagnetic storms, can have profound impacts on modern technology. These storms are triggered when a massive burst of solar wind and magnetic fields, often associated with a coronal mass ejection (CME), strikes the magnetopause. When the magnetopause is compressed by such an event, it can cause geomagnetic disturbances that ripple through the magnetosphere and ionosphere. These disturbances can disrupt GPS signals, cause power grid failures, and even endanger astronauts aboard the International Space Station (ISS). Understanding the dynamics of the magnetopause during these events is crucial for developing predictive models and mitigation strategies to protect technology and human life. Another fascinating aspect of the magnetopause is its role in particle acceleration. The boundary is not just a passive shield but an active participant in accelerating particles to high energies. This process occurs through a variety of mechanisms, including magnetic reconnection and wave-particle interactions. These accelerated particles can become part of Earth's radiation belts, also known as the Van Allen belts, which are regions of trapped high-energy particles surrounding the planet. The interaction between the magnetopause and the solar wind also generates a variety of waves and oscillations, such as Kelvin-Helmholtz waves. These waves occur when there is a velocity shear between two fluids or plasmas, much like the ripples formed on the surface of a river when it flows past a slower-moving body of water. At the magnetopause, these waves can grow to massive scales, influencing the transfer of energy and particles into the magnetosphere. The study of these waves is not just a theoretical exercise. It has practical implications for understanding plasma physics, a field that extends far beyond Earth's magnetosphere. Plasma, the fourth state of matter, makes up over 99% of the visible universe. By studying plasma behavior at the magnetopause, scientists gain insights that are applicable to everything from solar flares to the behavior of interstellar gas clouds. The magnetopause also plays a crucial role in the field of comparative planetology. By studying how similar boundaries function on other planets, scientists can draw parallels and distinctions that enhance our understanding of planetary systems. For instance, Mercury, the planet closest to the Sun, has a weak magnetic field and a magnetopause that is much closer to its surface than Earth's. This proximity makes Mercury's magnetosphere particularly vulnerable to the Sun's intense radiation and solar wind. On the other hand, gas giants like Jupiter and Saturn have magnetospheres that dwarf Earth's in size and strength. Jupiter's magnetopause, for example, is so large that it extends far beyond the orbits of some of its moons. The study of these planetary magnetospheres and their interactions with the solar wind provides valuable context for understanding Earth's magnetopause and its unique characteristics. The concept of the magnetopause extends beyond our solar system as well. In the search for exoplanets, the presence of a magnetosphere and a well-defined magnetopause is considered a potential indicator of habitability. A strong magnetic field can protect a planet's atmosphere from being stripped away by stellar winds, a fate that likely befell Mars. By studying the magnetopause, scientists can better assess the potential habitability of distant worlds. The magnetopause also holds clues to the mysteries of magnetic field reversals. Earth's magnetic field has flipped numerous times throughout its history, with the magnetic north and south poles swapping places. These reversals are recorded in the magnetic alignment of minerals and rocks, providing a timeline of Earth's magnetic history. Understanding how the magnetopause behaves during these reversals could offer insights into the mechanisms driving them and their implications for Earth's magnetosphere. As technology advances, our ability to study the magnetopause becomes increasingly sophisticated. Satellites equipped with advanced instruments can measure the magnetic field, plasma density, and particle flux with unprecedented precision. Missions like NASA's Magnetospheric Multiscale (MMS) and the European Space Agency's Solar Orbiter are pushing the boundaries of our understanding, revealing new details about the magnetopause's structure and behavior. The magnetopause is not just a boundary, it is a dynamic, living entity that responds to the Sun's rhythms and Earth's internal dynamics. It is a region of constant negotiation, where the forces of the cosmos meet the resilience of our planet. By studying this critical interface, we gain not only a deeper understanding of Earth's place in the solar system but also valuable insights into the universal processes that shape the cosmos. The magnetopause represents a frontier of constant discovery, where Earth's magnetic field and the solar wind engage in a never-ending dance of energy and matter. Beyond the mechanics of its function, this dynamic boundary invites us to contemplate the deeper mysteries of space physics and the unseen forces that govern our planet's resilience against the harshness of space. A fascinating aspect of the magnetopause is its dynamic and ever-changing nature. It is not a fixed structure. Instead, it ebbs and flows in response to the solar wind's intensity and the sun's activity. During periods of low solar activity, known as the solar minimum, the solar wind weakens, allowing the magnetopause to expand outward, giving Earth's magnetic field more room to extend. Conversely, during solar maximum, when the sun is most active, the magnetopause contracts under the increased pressure of the solar wind. These cycles of compression and expansion highlight the magnetopause's adaptability and its vital role in maintaining balance in an otherwise chaotic cosmic environment. One of the most critical processes occurring at the magnetopause is magnetic reconnection. This phenomenon is a cosmic-scale version of magnetic field lines snapping and rejoining, releasing immense amounts of energy in the process. Magnetic reconnection at the magnetopause allows some of the solar wind's energy and particles to enter the magnetosphere, fueling various space weather phenomena. It is a key mechanism that influences everything from auroras to geomagnetic storms and even the dynamics of Earth's radiation belts. Understanding magnetic reconnection is not only vital for comprehending Earth's magnetopause but also for interpreting processes throughout the universe. The same fundamental physics governs solar flares, coronal mass ejections, and even the behavior of plasma in distant astrophysical objects like neutron stars and black holes. By studying the magnetopause, scientists gain a microcosmic view of these universal phenomena. The magnetopause is also a natural laboratory for studying turbulence in plasmas. Plasma, the ionized state of matter, behaves in ways that challenge conventional understanding. Turbulence at the magnetopause results from the interaction of solar wind plasma with Earth's magnetic field, creating chaotic and complex flows of energy and particles. These turbulent interactions influence how solar wind energy is distributed throughout the magnetosphere, affecting space weather and Earth's upper atmosphere. Studying this turbulence is not just about understanding Earth's immediate environment. Plasma turbulence plays a role in galaxy formation, star formation, and the behavior of accretion disks around black holes. Insights gleaned from the magnetopause contribute to a broader understanding of these cosmic processes, emphasizing the interconnectedness of all celestial phenomena. The magnetopause also serves as a crucial line of defense against cosmic rays, high-energy particles originating from outside the solar system. While the solar wind deflects many of these particles, the magnetopause adds an additional layer of protection by guiding them around Earth. Without this combined defense, cosmic rays could wreak havoc on Earth's atmosphere and pose severe risks to life on the surface. However, the magnetopause's protective capabilities are not impenetrable. During particularly strong solar storms, the magnetopause can be pushed closer to Earth, exposing satellites and other space-based technologies to increased radiation. These events underscore the importance of monitoring and understanding the magnetopause's behavior to safeguard modern infrastructure. The role of the magnetopause extends beyond Earth's immediate environment. In the broader context of space exploration, it provides a template for understanding other planetary magnetospheres and their boundaries. Jupiter's magnetopause, for example, is a colossal structure shaped by the planet's intense magnetic field and the influence of its volcanic moon, Io. By comparing these systems, scientists can unravel the universal principles governing magnetospheric boundaries and their interactions with solar and stellar winds. The magnetopause also offers clues about the early history of our solar system. By studying its composition and behavior, scientists can infer how Earth's magnetic field has evolved over time. This, in turn, provides insights into the conditions that made Earth habitable. The magnetic field's strength and stability are essential for retaining the atmosphere and shielding the planet from harmful radiation, both critical factors for the development and sustenance of life. As humanity looks beyond Earth, understanding the magnetopause has implications for the search for life on other planets. A strong magnetic field and a well-defined magnetopause are considered indicators of a planet's ability to sustain an atmosphere and protect potential biospheres. By studying Earth's magnetopause, scientists refine the criteria for identifying habitable exoplanets and assessing their potential to support life. The magnetopause is also a bridge between science and technology. Instruments like magnetometers, particle detectors, and plasma analyzers, developed to study the magnetopause, have applications far beyond space exploration. These technologies are used in industries ranging from telecommunications to healthcare, demonstrating the tangible benefits of studying this elusive boundary. In recent years, missions like NASA's Themis and ESA's Cluster have provided unprecedented insights into the magnetopause. These spacecraft are equipped with advanced sensors that measure the magnetic field, plasma density, and particle velocities with remarkable precision. The data collected has revealed new details about the magnetopause's structure, dynamics, and interactions with the solar wind, pushing the boundaries of our understanding. The magnetopause remains a symbol of the interplay between chaos and order, vulnerability and resilience. It is a boundary that protects, adapts, and reveals the intricate dance of forces that shape our cosmic environment. As we continue to explore its mysteries, we uncover not just the secrets of Earth's magnetic shield but also the universal principles that govern the cosmos. The magnetopause stands as a frontier where Earth's invisible shield, its magnetic field, interacts with the relentless solar wind, forming a complex yet harmonious interplay of forces. This boundary, though imperceptible to the naked eye, holds the key to understanding not only our planet's protection mechanisms, but also the profound physics that govern the universe. As we delve deeper, the magnetopause reveals its layered structure and dynamic nature. It consists of several key regions: the bow shock, the magnetosheath, and the inner magnetosphere. Each plays a unique role in mitigating the effects of the solar wind. The bow shock is the first line of defense, where the solar wind slows down abruptly upon encountering Earth's magnetic field. This sudden deceleration causes the particles to heat up, creating a turbulent zone. Behind the bow shock lies the magnetosheath, a buffer region where the solar wind is further slowed and redirected around the planet. The magnetosphere itself houses the magnetopause, marking the outermost boundary where Earth's magnetic field still holds sway. This layering allows the system to absorb, deflect, and manage the immense energy carried by the solar wind. The structure of the magnetopause adapts continuously to changes in the solar wind's intensity and direction. One intriguing phenomenon associated with the magnetopause is the Kelvin-Helmholtz instability. This occurs when there is a velocity shear between two fluid-like regions, in this case, the solar wind and Earth's magnetosphere. The result is the formation of rolling waves at the magnetopause, resembling ocean waves breaking along the shoreline. These waves create turbulence and allow energy and particles to cross the boundary, influencing the overall behavior of the magnetosphere. Such processes are critical for understanding space weather, as they determine how solar wind energy penetrates Earth's magnetic defenses. The impact of space weather extends beyond auroras. It can disrupt communication systems, damage satellites, and even threaten power grids on the ground. The magnetopause, therefore, is not just a passive boundary but an active player in managing these effects. The magnetopause's behavior during geomagnetic storms is particularly fascinating. When a coronal mass ejection, CME, or a strong solar wind stream reaches Earth, the increased pressure compresses the magnetopause closer to the planet. In extreme cases, it can push the boundary within geosynchronous orbit, exposing satellites to heightened radiation levels. During these events, the magnetopause becomes a battleground, absorbing and redistributing the energy from the Sun to minimize its impact on Earth. Auroras, the shimmering lights that adorn polar skies, owe their existence to interactions at the magnetopause. When magnetic reconnection occurs, it allows solar wind particles to enter the magnetosphere, where they are guided along magnetic field lines toward the poles. Upon colliding with atmospheric particles, these high-energy particles release photons, creating the spectacular light shows. However, the magnetopause is not just an Earth-centric phenomenon. Other planets with magnetic fields, such as Jupiter and Saturn, have their own magnetopauses, shaped by their unique magnetic properties and interactions with the solar wind. Jupiter's magnetopause, for example, is far larger than Earth's due to its immense magnetic field and rapid rotation. These comparative studies provide valuable insights into the universal principles of magnetospheric physics. Additionally, the magnetopause serves as a window into the Sun's behavior. By studying how the magnetopause responds to changes in the solar wind, scientists can infer details about solar activity, including the strength and frequency of solar flares and CMEs. This knowledge is crucial for predicting space weather and mitigating its effects on technology and human activities. Technological advancements have enabled more detailed exploration of the magnetopause. Missions like NASA's Magnetospheric Multiscale, MMS, have provided high-resolution data on magnetic reconnection, revealing its role in shaping the magnetopause's dynamics. MMS findings have deepened our understanding of energy transfer processes, offering a glimpse into the mechanics of plasma behavior at the smallest scales. The study of the magnetopause also informs our search for habitable planets beyond our solar system. A strong magnetosphere and a stable magnetopause are indicators of a planet's ability to retain an atmosphere and protect potential life from harmful radiation. By understanding how Earth's magnetopause operates, we refine the criteria for assessing exoplanet habitability. Moreover, the magnetopause offers a philosophical perspective on Earth's place in the universe. It reminds us of the delicate balance between vulnerability and resilience, chaos and order. The forces at play at the magnetopause are a testament to the interconnectedness of all things, from the Sun's fiery surface to the atmospheric particles that sustain life on Earth. As we continue to study the magnetopause, we uncover new layers of complexity and beauty. Its role as a dynamic shield, a conduit for energy, and a stage for cosmic phenomena highlights the intricate interplay of forces that sustain our world. The magnetopause is not just a boundary, it is a gateway to understanding the fundamental principles that shape our universe. Through missions, observations, and theoretical models, the mysteries of the magnetopause are gradually being unraveled. Each discovery not only enhances our knowledge of Earth's magnetic shield but also deepens our appreciation for the extraordinary mechanisms that enable life to thrive on this small blue planet. The journey to understand the magnetopause is far from over. As technology advances and our curiosity grows, so too will our ability to explore this enigmatic frontier. The magnetopause invites us to push the boundaries of knowledge, to seek connections between the seen and unseen, and to embrace the wonder of a universe that is both protective and challenging. The magnetopause, as a cosmic intersection, embodies a delicate balance between order and chaos. The constant tug-of-war between the solar wind and Earth's magnetic field demonstrates the perpetual dynamism of our planet's protective systems. This interplay has fascinated scientists for decades, as it reveals not only the nature of Earth's defenses but also the profound complexities of plasma physics and electromagnetic interactions on a cosmic scale. The magnetic reconnection process at the magnetopause is one of the most intriguing phenomena. When opposing magnetic fields interact, they can break and reconnect in a violent release of energy. This process facilitates the transfer of solar wind particles and energy into the magnetosphere. It's as if the magnetopause, while protecting the Earth, occasionally lets down its guard, allowing the Sun's energy to mingle with our planet's magnetic environment. This reconnection is not a smooth, uniform event, it happens in bursts, forming localized regions of intense activity. These regions, called magnetic islands, become hotbeds of energy exchange and plasma acceleration. They play a crucial role in driving geomagnetic storms, which can have far-reaching impacts on Earth's technological infrastructure. Consider the magnetopause during a solar storm. When a powerful coronal mass ejection, CME, from the Sun collides with Earth's magnetic field, the magnetopause is pushed inward, compressing and intensifying. This compression amplifies the processes of magnetic reconnection, creating cascading effects throughout the magnetosphere. Energetic particles are accelerated and funneled toward the poles, triggering vivid auroras but also posing risks to satellites, astronauts, and power grids. Yet, the magnetopause isn't merely reactive, it also acts as a regulator. Its dynamic adaptability ensures that Earth's magnetic shield remains effective despite the Sun's changing behavior. This adaptability is a reminder of the resilience of natural systems, which can absorb and adapt to external pressures in ways that sustain balance and stability. Understanding the magnetopause has required innovative approaches and cutting-edge technology. Instruments aboard spacecraft like the Magnetospheric Multiscale (MMS) mission have revolutionized our ability to study this boundary in unprecedented detail. MMS uses multiple spacecraft flying in close formation to create a three-dimensional picture of the magnetopause, capturing data on magnetic reconnection, turbulence, and particle dynamics at microsecond timescales. This high-resolution data has confirmed theories about reconnection and revealed surprising new behaviors, such as rapid particle jets and turbulent eddies that ripple through the magnetopause. These findings are reshaping our understanding of plasma physics, not only in Earth's magnetosphere but also in other astrophysical systems, from the atmospheres of distant exoplanets to the magnetospheres of stars. The magnetopause also serves as a training ground for testing technologies and models that can be applied to other celestial bodies. For instance, the magnetospheres of Jupiter and Saturn, with their immense size and unique dynamics, offer opportunities to compare and contrast with Earth's. Studying their magnetopauses helps scientists refine universal principles of magnetic field interactions and assess the habitability of moons like Europa and Enceladus, which are bathed in their host planets' magnetospheres. Even beyond our solar system, the principles governing the magnetopause inform the search for habitable exoplanets. A planet's ability to sustain life depends in part on its capacity to shield its atmosphere from stellar winds. The presence of a magnetopause indicates that the planet possesses a magnetic field robust enough to fend off these forces, preserving its atmosphere and water, key ingredients for life. The magnetopause also offers insight into the origins of our solar system. By studying how the solar wind interacts with magnetic fields, scientists can infer details about the young sun and the conditions that shaped the early Earth. This knowledge helps to reconstruct the processes that led to the formation of the magnetosphere, atmosphere, and the conditions necessary for life. But the magnetopause isn't just about protection, it's also a gateway. It allows some solar wind particles to penetrate and interact with Earth's magnetosphere, a process that drives the dynamic behavior of the Van Allen radiation belts and influences space weather. These interactions are a double-edged sword. While they create breathtaking auroras, they also generate high-energy radiation that can damage satellites and endanger astronauts. One of the most fascinating aspects of the magnetopause is its role in connecting Earth to the vast expanse of interplanetary space. The boundary marks the point where Earth's influence wanes and the Sun's dominance begins. This transition zone is a reminder that our planet is not isolated but deeply connected to the cosmos, its fate intertwined with the behavior of the Sun and the forces of the universe. The study of the magnetopause is a journey into the heart of these connections. It challenges us to think beyond Earth's surface and consider the invisible forces that shape our environment. It also underscores the importance of protecting our technological infrastructure, as our reliance on satellites and power grids makes us increasingly vulnerable to the effects of space weather. Despite decades of research, the magnetopause continues to surprise and inspire. Its dynamic nature and the mysteries it holds are a testament to the complexity of the universe and the ingenuity of human exploration. Each new discovery about the magnetopause not only enhances our understanding of Earth's magnetic field but also deepens our appreciation for the interconnectedness of all things. As we look to the future, the study of the magnetopause will undoubtedly play a key role in advancing space science. It will inform the development of new technologies, guide the exploration of other planets, and help us prepare for the challenges of living in an increasingly spacefaring civilization. The magnetopause is more than just a boundary, it is a symbol of resilience, adaptation, and the enduring quest for knowledge. It reminds us that even in the face of relentless forces, there is strength in balance and beauty in complexity. The magnetopause, with all its intricacies, continues to be a frontier of scientific discovery that not only sheds light on Earth's immediate space environment but also extends our understanding of the cosmos at large. The more we delve into this fascinating boundary, the more we realize how interconnected our planet is with the broader universe, and how its interactions reveal deeper truths about the fundamental forces at play. One of the intriguing questions researchers face is the variability of the magnetopause. Unlike a static barrier, the magnetopause is dynamic, pulsating in response to changes in the solar wind's speed, density, and magnetic orientation. These pulsations are not random. They follow complex patterns that reflect the balance of forces acting upon the Earth's magnetic field. The Kelvin-Helmholtz instability, for example, manifests as wave-like motions along the magnetopause when there is a velocity difference between the solar wind and the magnetosphere. These waves create vortices, regions of turbulence where plasma mixing occurs. This turbulence has far-reaching implications. It influences the distribution of energetic particles in Earth's radiation belts, modulates auroral displays, and drives currents in the magnetosphere that can affect ground-based electrical systems. Understanding these turbulent interactions is critical, as they offer a window into the chaotic yet ordered nature of plasma physics. Adding to this complexity is the role of the interplanetary magnetic field, IMF, a component of the Sun's magnetic field carried through space by the solar wind. When the IMF is aligned opposite to Earth's magnetic field, a condition called southward IMF, magnetic reconnection at the magnetopause becomes highly efficient. This alignment creates a direct channel for energy and particles to flow into the magnetosphere, enhancing geomagnetic activity. The magnetopause's ability to modulate these interactions demonstrates its role as both a shield and a conduit. It filters harmful solar radiation while simultaneously enabling the exchange of energy that sustains Earth's dynamic magnetospheric processes. This dual role highlights the fine balance maintained by natural systems, where protection and interaction coexist. Exploring the magnetopause has also pushed the boundaries of technology and innovation. Spacecraft missions like MMS, Themis, time history of events and macro-scale interactions during substorms, and Cluster have revolutionized our understanding of this boundary. These missions employ constellations of spacecraft to capture multi-point measurements, providing a detailed, three-dimensional perspective of the magnetopause. These technological advances have revealed phenomena that were once theoretical. For instance, the detection of electron-scale reconnection has confirmed that even at the smallest scales, the magnetopause is a site of intense energy transformation. This discovery bridges the gap between macroscopic and microscopic plasma behaviors, offering insights that extend beyond Earth to other magnetized systems in the universe. The magnetopause also holds keys to understanding space weather, a term that encompasses the Sun's impact on Earth's space environment. Space weather events, such as geomagnetic storms and solar flares, originate from interactions at the magnetopause. Predicting these events requires a deep understanding of how solar wind conditions influence the magnetosphere's dynamics. This predictive capability is vital for protecting modern infrastructure. Satellites, power grids, and communication networks are all vulnerable to the effects of space weather. Severe geomagnetic storms can induce currents in power lines, causing widespread blackouts, while high-energy particles can damage satellite electronics and pose health risks to astronauts. Studying the magnetopause also has practical implications for space exploration. As humanity ventures further into the solar system, understanding the dynamics of planetary magnetospheres becomes increasingly important. Mars, for example, lacks a global magnetic field, leaving its thin atmosphere exposed to the solar wind. By comparing Mars' interaction with the solar wind to Earth's, scientists can infer the protective role of a magnetopause and assess the challenges of colonizing planets without such shields. The lessons learned from Earth's magnetopause are also applied to understanding the habitability of exoplanets. A strong magnetic field and a well-defined magnetopause are considered indicators of a planet's ability to sustain an atmosphere and protect surface conditions conducive to life. These factors are integral to the search for extraterrestrial life, guiding the selection of exoplanets for detailed study. Beyond practical applications, the magnetopause invites us to ponder profound questions about the universe. It challenges us to consider the interplay of forces that shape our environment and the delicate balance that sustains life on Earth. It also underscores the beauty of natural systems, where complexity arises from simple interactions governed by universal laws. The ongoing exploration of the magnetopause is a testament to human curiosity and ingenuity. Each new discovery not only enhances our understanding of Earth's space environment, but also contributes to the broader quest for knowledge about the cosmos. The magnetopause, with its dynamic nature and far-reaching connections, is a reminder of the interconnectedness of all things, a bridge between Earth and the infinite expanse beyond. As we continue to unravel its mysteries, the magnetopause stands as a symbol of resilience and adaptation, reflecting the enduring relationship between our planet and the Sun. It inspires us to look beyond our immediate surroundings and embrace the wonder of the universe, where even the smallest interactions can reveal the grandest truths. This vast exploration of the magnetopause brings us closer to understanding not just the natural world around us but the intricate mechanisms of the universe itself. The magnetopause serves as a reminder that Earth's relationship with space is far from static. It's a dynamic dance, a perpetual balancing act between protection and vulnerability, chaos and order, and ultimately, life and destruction. One particularly fascinating aspect of the magnetopause is its role as a natural laboratory for studying universal processes. The physics of plasmas, magnetic reconnection, and particle acceleration that occur at the magnetopause are not unique to Earth. They mirror phenomena occurring throughout the cosmos, from the atmospheres of distant stars to the edges of black holes. By studying the magnetopause in great detail, scientists unlock secrets that can be applied to understanding these far-off celestial events. Consider, for example, the process of magnetic reconnection. It occurs when two opposing magnetic fields come into contact, breaking and reforming in a new configuration. This process releases massive amounts of energy and accelerates particles to incredible speeds. On Earth, reconnection at the magnetopause drives auroral activity and influences the dynamics of the magnetosphere. In space, it plays a crucial role in the formation of solar flares, the behavior of pulsars, and the shaping of interstellar magnetic fields. Reconnection is not just a localized phenomenon, it is a fundamental process shaping the universe. Understanding its mechanics here at Earth's magnetopause offers insight into how similar processes unfold on a cosmic scale. This connection between local and universal physics highlights the profound importance of studying Earth's space environment. It's not just about understanding our immediate surroundings, but also about deciphering the mysteries of the cosmos. Another area of intrigue lies in the boundary's ability to create and sustain currents. As solar wind plasma flows past the magnetopause, it generates electric currents that travel along magnetic field lines. These currents, known as field-aligned currents or Birkeland currents, connect the magnetopause to Earth's ionosphere. They influence phenomena such as the auroras and contribute to the complex electrical circuits within the magnetosphere. What's remarkable is the scale and complexity of these currents. They carry immense amounts of energy and interact with countless other processes within the magnetosphere. They are, in essence, the lifeblood of Earth's magnetic environment, sustaining its dynamic nature and linking various regions of space and atmosphere in a tightly coupled system. Studying these currents has also revealed the intricate choreography of Earth's space environment. They show how energy flows between the Sun, the magnetosphere, and the atmosphere, creating a dynamic system that is constantly adjusting and rebalancing itself. This self-regulating nature of the magnetosphere underscores the resilience of natural systems and their ability to adapt to changing conditions. The magnetopause also offers a unique perspective on time and scale in the universe. The interactions occurring at this boundary unfold on timescales ranging from milliseconds to hours and cover distances from a few kilometers to tens of thousands of kilometers. These variations remind us that nature operates on multiple levels simultaneously, with processes on vastly different scales influencing one another in profound ways. For instance, small-scale turbulence at the magnetopause can have large-scale effects on the entire magnetosphere. These cascading interactions demonstrate the interconnectedness of natural systems and challenge us to think beyond linear cause and effect relationships. They also highlight the importance of studying the magnetopause as a whole, rather than focusing solely on individual phenomena. As we continue to explore the magnetopause, new technologies are opening doors to previously unimagined discoveries. Advanced spacecraft equipped with cutting-edge instruments are providing high-resolution measurements of the boundary's structure and behavior. Simultaneously, computer simulations are allowing scientists to model the magnetopause in unprecedented detail, recreating its interactions with the solar wind and magnetosphere. These tools are not only expanding our knowledge but also inspiring new questions. How does the magnetopause respond to extreme solar events, such as coronal mass ejections or solar superstorms? What role does the magnetopause play in the long-term evolution of Earth's magnetic field? How do conditions at the magnetopause compare to those at other planetary magnetospheres, such as Jupiter or Saturn? The answers to these questions will not only deepen our understanding of the magnetopause but also provide broader insights into the nature of space and time. They will help us appreciate the intricate tapestry of forces and interactions that shape our universe and reveal the hidden connections between seemingly disparate phenomena. The magnetopause is not just a boundary, it's a portal to understanding the fundamental processes that govern our world and the cosmos. It challenges us to think big, to look beyond the familiar, and to embrace the unknown. It reminds us that even the most complex systems are governed by simple, elegant principles, and that by studying these principles, we can unlock the secrets of the universe itself. As we stand on the cusp of new discoveries, the magnetopause beckons us to continue exploring, questioning, and learning. It invites us to push the boundaries of our knowledge and to embrace the wonder and mystery of the natural world. And in doing so, it reminds us of our place in the vast, interconnected web of existence, a place where every discovery brings us closer to understanding the infinite beauty of the cosmos. The story of the magnetopause is far from over, as it serves as a focal point for some of the most ambitious and groundbreaking scientific endeavors in human history. Each new discovery, each new layer of understanding, brings us closer to unraveling the complexities of not only our planet's magnetic environment, but also the mechanisms that drive the universe itself. The magnetopause, with its dynamic and ever-shifting nature, stands as a testament to the intricate balance of forces at play in the natural world. One area of active research involves the long-term effects of solar activity on the magnetopause. The Sun operates on an 11-year solar cycle, during which its magnetic activity rises and falls. Solar maximums, periods of heightened solar activity, bring an increased frequency of solar flares and coronal mass ejections, CMEs. These events hurl massive amounts of charged particles toward Earth, creating immense pressure on the magnetopause and compressing it significantly closer to the planet. During these times, the magnetopause can move from its average distance of approximately 10 Earth radii down to as close as 6 Earth radii. This compression not only impacts the magnetosphere but also enhances the risk of geomagnetic storms that can disrupt communication systems, satellites, and power grids on Earth. Understanding how the magnetopause behaves under such extreme conditions is crucial for mitigating these risks and safeguarding modern infrastructure. Conversely, during solar minimums, when solar activity is at its lowest, the magnetopause extends farther into space, allowing for different kinds of interactions with the solar wind. These quieter periods provide scientists with unique opportunities to study the baseline behavior of the magnetopause without the added complexity of heightened solar activity. By comparing data from both solar maximums and minimums, researchers can develop a more comprehensive understanding of the magnetopause's dynamics and its role in the broader space weather system. The magnetopause is also central to the study of energetic particle dynamics in Earth's magnetosphere. One of the most intriguing phenomena is the formation and behavior of the Van Allen radiation belts, two concentric zones of charged particles trapped by Earth's magnetic field. The outer belt, in particular, is strongly influenced by processes occurring at the magnetopause. When the magnetopause is disturbed by solar wind pressure or magnetic reconnection, it can inject high-energy particles into the outer radiation belt, increasing its intensity. These particle injections can pose significant hazards to spacecraft, astronauts, and even high-altitude aviation. By studying how the magnetopause regulates the flow of these particles, scientists hope to develop predictive models that can warn of increased radiation levels, potentially saving lives and billions of dollars in damage to critical infrastructure. The influence of the magnetopause extends beyond Earth. Comparative studies of other planetary magnetospheres, such as those of Jupiter, Saturn, and Mercury, reveal striking similarities and differences in how magnetopauses interact with their respective solar winds. Jupiter's magnetopause, for instance, is the largest in the solar system, with a boundary that can extend over 100 times the radius of the planet. This vast scale is due to Jupiter's powerful magnetic field and its interaction with the Sun's wind. These comparative studies provide valuable context for understanding Earth's magnetopause. They highlight how factors like a planet's magnetic field strength, rotation rate, and distance from the Sun influence the structure and behavior of its magnetopause. They also offer a glimpse into the diversity of magnetic environments in the solar system, helping us appreciate the unique characteristics of our own planet's protective shield. The magnetopause also plays a critical role in the search for life beyond Earth. Exoplanets with strong magnetic fields and well-defined magnetopauses are considered more likely to harbor life, as these features protect planetary atmospheres from being stripped away by stellar winds. The study of the magnetopause thus has direct implications for astrobiology and the ongoing quest to identify habitable worlds in distant star systems. Technological advances continue to drive our understanding of the magnetopause to new heights. Missions like the Magnetospheric Multiscale (MMS) mission have provided unprecedented insights into the small-scale processes occurring at the magnetopause, such as electron diffusion regions during magnetic reconnection. These discoveries not only deepen our understanding of Earth's space environment, but also inform theories about magnetic phenomena throughout the universe. Looking ahead, upcoming missions and observational tools promise to expand our knowledge even further. Advances in satellite technology, computational modeling, and artificial intelligence are enabling scientists to analyze vast amounts of data with unparalleled precision. These tools are uncovering patterns and correlations that were previously invisible, providing a more holistic view of the magnetopause and its role in the Sun-Earth system. Yet, for all our advancements, the magnetopause remains a place of wonder and mystery. Its dynamic nature, driven by the interplay of countless forces, challenges us to rethink our assumptions and push the boundaries of what we know. It reminds us that the universe is a complex, interconnected web of phenomena, where every discovery leads to new questions and deeper insights. The magnetopause is not just a boundary, it's a gateway to understanding the fundamental processes that shape our planet, our solar system, and the cosmos at large. Its study is a testament to human curiosity, ingenuity, and the relentless pursuit of knowledge. And as we continue to explore its mysteries, we are reminded of our place in the universe, a small but significant part of a vast and ever-changing cosmic dance. The ongoing exploration of the magnetopause not only furthers our understanding of space but also enhances our technological capabilities. By studying this boundary and its interactions with the solar wind, scientists have gained valuable insights into the behavior of plasma and magnetic fields. These discoveries are crucial for developing better space weather forecasting models, improving satellite technology, and ensuring the safety of astronauts in deep space. One of the most intriguing aspects of the magnetopause is its potential to influence space weather on Earth. While the magnetosphere protects us from the harshest effects of solar radiation, it is not an impenetrable shield. The magnetopause plays a crucial role in determining the intensity and frequency of geomagnetic storms, which can have far-reaching effects on communications, navigation, and power systems. During periods of intense solar activity, such as solar flares or CMEs, the magnetopause can become compressed or distorted, allowing solar wind particles to penetrate deeper into Earth's magnetic field. This can lead to an increased likelihood of geomagnetic storms, which can disrupt satellite operations, radio communications, and even cause power outages on the ground. The study of the magnetopause's response to such events is vital for mitigating these risks and developing better protective measures for both technological systems and human life. Geomagnetic storms are a natural phenomenon, but their effects on modern society are becoming more pronounced as we become increasingly reliant on satellite-based technologies. With the growing prevalence of GPS systems, telecommunications satellites, and space-based observatories, understanding the behavior of the magnetopause is crucial for ensuring the resilience of these technologies. By improving our ability to predict and prepare for space weather events, we can better safeguard our technological infrastructure and reduce the economic and social impacts of solar storms. Another area of interest lies in the magnetopause's ability to interact with the ionosphere. The ionosphere is the layer of Earth's atmosphere that is ionized by solar radiation and plays a crucial role in radio communication, GPS, and the transmission of electrical signals. The magnetopause is closely linked to the ionosphere, as it helps regulate the flow of solar wind particles and determines the extent of their interaction with the atmosphere. When the magnetopause is compressed or disturbed by solar wind pressure, it can lead to an increase in ionospheric activity, resulting in phenomena such as auroras, geomagnetic storms, and ionospheric scintillation. These effects can interfere with radio signals and GPS accuracy, particularly at high latitudes. Understanding the magnetopause's role in modulating ionospheric conditions is key to improving communication and navigation systems, especially in regions where space weather events are more frequent. The magnetopause also offers a unique opportunity to study plasma physics, which is fundamental to many processes in space and astrophysics. Plasma, the fourth state of matter, is made up of charged particles that are influenced by electromagnetic fields. The interactions between these particles at the magnetopause provide a natural laboratory for studying plasma behavior in extreme conditions. Researchers can use data from spacecraft and ground-based observatories to analyze how plasma flows, how magnetic fields evolve, and how energy is transferred across boundaries in space. These studies have broader implications for understanding other astrophysical phenomena, such as the behavior of solar flares, the dynamics of supernovae, and the structure of interstellar magnetic fields. By studying the magnetopause as a natural plasma laboratory, scientists are able to test theories and refine models that can be applied to more distant regions of the universe. While the magnetopause may seem like an isolated phenomenon, it is part of a much larger cosmic framework. As our understanding of this boundary deepens, we are beginning to recognize its connection to other parts of the solar system, the galaxy, and beyond. The magnetopause serves as a reminder that Earth is not a static entity, but rather a dynamic part of the greater cosmic system, constantly interacting with the Sun, other planets, and the broader universe. Our continued exploration of the magnetopause is not just about understanding the space around us, it's about understanding the universe itself. As we study the interactions between the solar wind, the magnetopause, and Earth's magnetic field, we are learning more about the fundamental forces that govern the cosmos. We are discovering how planets, stars, and even galaxies interact with their surroundings and how these interactions shape the evolution of the universe. This process of discovery is ongoing, and each new finding brings us closer to understanding the nature of space, time, and energy. With each advancement in technology, we are able to study the magnetopause in greater detail, unveiling new layers of complexity and opening doors to further exploration. We are no longer just observers of space, we are participants in a grand cosmic experiment, uncovering the mysteries of the universe one discovery at a time. The study of the magnetopause also reminds us of the importance of collaboration and innovation in science. The data that has been gathered over the years has come from a wide range of instruments, missions, and research efforts, each contributing to the larger picture. From satellite measurements to ground-based observations, from theoretical modeling to practical applications, the study of the magnetopause is a testament to the power of human ingenuity and teamwork. Looking to the future, the magnetopause will continue to be a focal point for scientific research. New missions, new technologies, and new techniques will allow us to probe deeper into its mysteries and uncover even more secrets about our planet's interaction with the Sun and space weather. Each new discovery will build on the knowledge of the past, bringing us closer to a comprehensive understanding of the forces that shape the Earth's magnetic environment and its place in the universe. Ultimately, the study of the magnetopause is more than just a scientific pursuit, it is a quest for knowledge that connects us to the cosmos. It reminds us of the beauty and complexity of the universe and our role within it. As we continue to explore this boundary, we are not only learning about the forces that protect us but also about the forces that shape the very fabric of existence itself. And as we push the boundaries of discovery, we are reminded that the universe is vast, mysterious, and full of infinite possibilities waiting to be uncovered. As our understanding of the magnetopause grows, it opens the door to a broader view of the forces that shape not only Earth but also the broader solar system. The interactions between the solar wind, the magnetosphere, and the magnetopause offer a unique opportunity to study the delicate balance of forces that protect Earth from harmful solar radiation. These forces, while seemingly invisible and intangible, are a testament to the complexity of space weather and the universe itself. The magnetopause itself is constantly changing. The solar wind, which continuously flows from the Sun, varies in strength and intensity depending on solar activity. During periods of increased solar activity, such as during solar flares or coronal mass ejections, the solar wind is more powerful, which can result in the magnetopause being compressed, causing the magnetic field to interact with the solar wind more directly. On the other hand, when solar activity is quieter, the magnetopause can expand, creating a larger shield between Earth and the solar wind. This dynamic nature of the magnetopause plays a crucial role in regulating the Earth's space environment. It is not a static shield, but rather a constantly shifting boundary that adjusts based on the conditions of the Sun and the behavior of the solar wind. In times of heightened solar activity, the magnetopause becomes a battleground of sorts, where solar wind particles push against Earth's magnetic field, trying to break through. The Earth's magnetic field fights back, but in extreme cases, some particles may slip through the magnetopause and affect the planet's atmosphere, resulting in phenomena like auroras and geomagnetic storms. While geomagnetic storms are a well-known consequence of solar-wind interactions, the magnetopause is also tied to a broader, more mysterious phenomenon: space weather. Space weather refers to the interaction between the Sun's activity and the magnetic environment of planets, satellites, and even interstellar space. These interactions can have far-reaching effects on technology, as well as human health. Space weather can cause disruptions to satellite communications, GPS systems, and power grids, while also posing a risk to astronauts exposed to heightened radiation levels. As technology becomes more advanced, it is essential to improve our ability to predict and monitor space weather. By continuing to study the magnetopause and its relationship with the solar wind, scientists are developing better models to predict when these space weather events will occur and how they might affect Earth. This research is critical for improving the resilience of technology and infrastructure in the face of increasing solar activity. By understanding how the magnetopause behaves during different conditions, we can better prepare for solar events and mitigate their potential impacts on our technological systems. The magnetopause's influence extends far beyond Earth's atmosphere, affecting not only the planet but also the Moon, Mars, and other planets in the solar system. For example, the magnetosphere of Mars is much weaker than Earth's, and it does not have a significant magnetopause to protect it from solar wind. This lack of protection has contributed to the stripping away of the Martian atmosphere over billions of years. The study of how different planets' magnetic fields interact with the solar wind offers valuable insights into planetary evolution and the potential for habitability on other worlds. While Earth's magnetopause is a protective shield, it also serves as a natural laboratory for studying the behavior of plasma, magnetic fields, and radiation. Understanding how the magnetopause responds to solar wind, solar flares, and other cosmic events can reveal valuable information about the fundamental forces that govern space. For instance, studying how the magnetosphere shields Earth from solar wind particles can help scientists better understand the behavior of other cosmic bodies, such as exoplanets, and their potential for supporting life. One fascinating aspect of the magnetopause is its ability to reflect and transmit solar wind particles. In some instances, solar wind particles are reflected back into space by the magnetopause, while in others, they are allowed to enter Earth's magnetic field. The balance between these two processes is determined by the strength of the solar wind, the configuration of Earth's magnetic field, and the pressure exerted by the solar wind. This dynamic process helps regulate the flow of solar radiation and ensures that Earth remains shielded from harmful particles. Scientists use a variety of tools to study the magnetopause, including satellite missions such as NASA's Magnetospheric Multiscale (MMS) mission, which is specifically designed to investigate the interactions between the solar wind and the magnetosphere. These satellites measure the energy, speed, and direction of particles within the magnetosphere, providing crucial data for understanding how solar wind and magnetic fields interact at the magnetopause. These measurements allow scientists to study the magnetopause in real time, helping to refine our models of space weather and improve predictions of solar activity. The magnetopause's ability to protect Earth from harmful solar radiation is one of the primary reasons why life on our planet can exist. Without this protective shield, Earth would be exposed to the full brunt of the solar wind, which could strip away the atmosphere and leave the planet vulnerable to radiation. The existence of the magnetopause is a testament to the delicate balance of forces that make Earth's environment so unique and conducive to life. It serves as a reminder of how interconnected and dependent we are on the various forces that govern the universe. As we continue to explore the mysteries of the magnetopause, scientists hope to gain further insights into its behavior and how it interacts with the solar wind. This research is not only crucial for protecting Earth's technological infrastructure, but also for understanding the fundamental workings of space weather, plasma physics, and planetary science. The magnetopause offers a window into the dynamic processes that shape our planet's magnetic environment and provides clues to understanding the broader behavior of the cosmos. The study of space weather and the magnetopause is a rapidly evolving field. As space missions become more sophisticated and our understanding of the Sun's activity grows, we are gaining new insights into the nature of space weather and how it affects the Earth. The magnetopause remains a focal point for future research, and its study will continue to yield new discoveries that could reshape our understanding of space, time, and the forces that govern our universe. The magnetopause is not just a boundary in space, it is a reminder of how interconnected our planet is with the broader solar system. It is a symbol of the forces that shape not only Earth's environment, but also our understanding of the cosmos. As we explore the mysteries of the magnetopause, we are learning more about the Sun, the solar wind, and the fundamental forces that govern the universe. Each new discovery brings us closer to understanding the forces that shape our world and our place in the cosmos. Continuing from where we left off, the magnetopause is more than just an invisible shield that protects Earth. It serves as an essential gateway for understanding how the solar system works and the broader forces that influence all planetary bodies. Its dynamic nature provides a glimpse into the ever-changing relationships between planets, stars, and the cosmic forces that govern the universe. As we look at the magnetopause and its interactions with the solar wind, we can also see the potential implications for humanity's future space exploration efforts. The magnetopause plays a crucial role in how we would protect astronauts on long-duration missions beyond Earth's magnetic field. Once humans leave the protective embrace of Earth's magnetosphere, they will be exposed to higher levels of radiation from the Sun and cosmic rays. This is particularly relevant as NASA and other space agencies plan future manned missions to the Moon, Mars, and beyond. Understanding the magnetopause's role in shielding Earth from solar radiation is a critical step in developing technologies that can protect astronauts from these dangers. The study of the magnetopause also provides us with valuable insights into other solar system bodies, particularly those without a strong magnetic field. Take, for instance, Venus. Unlike Earth, Venus has no global magnetic field to protect it from solar wind. The lack of a magnetopause means that the solar wind strips away the planet's atmosphere over time. Understanding these processes on Venus could help scientists learn more about how other planets in our solar system evolved and how they might have supported life in the past, or could potentially do so in the future. Mars offers another fascinating comparison. While Mars does have a thin magnetic field, it is not nearly as powerful as Earth's. Mars' magnetic field is localized, and there is no global magnetosphere to shield the planet from solar wind. As a result, the Martian atmosphere has been slowly stripped away over millions of years, leaving the planet vulnerable to the Sun's harsh radiation. This serves as a stark reminder of the crucial role that magnetic fields play in protecting planetary environments. Space agencies are using this knowledge to design technologies and strategies to protect both astronauts and spacecraft from the dangers of space weather. One solution being investigated is the creation of artificial magnetic fields, which could shield space habitats from harmful radiation. These artificial fields could mimic the protective qualities of Earth's magnetopause, ensuring that astronauts remain safe even in environments with little to no natural magnetic protection. Understanding the magnetopause's relationship with the solar wind is also fundamental to understanding space weather patterns, which can have significant consequences for Earth's technological infrastructure. From satellites to power grids, our reliance on space-based technology makes us vulnerable to disruptions caused by solar storms. In extreme cases, solar flares and coronal mass ejections can cause geomagnetic storms, which in turn can induce power surges, damage satellites, and even disrupt communication networks. The magnetopause's role in protecting Earth's atmosphere from these cosmic phenomena is essential to mitigating the potential damage caused by space weather. The magnetopause's influence also extends to the broader field of astrophysics. By studying how the solar wind interacts with Earth's magnetic field, scientists can learn more about the behavior of plasma and magnetic fields throughout the universe. These findings have the potential to unlock new mysteries about distant stars, black holes, and other celestial bodies. As we look further into the universe, understanding the interactions between magnetic fields and charged particles could offer insights into the workings of far-off systems and the nature of cosmic events such as solar flares, supernovae, and even the formation of galaxies. Moreover, the study of the magnetopause sheds light on the broader context of planetary habitability. The existence of a protective magnetic field plays a key role in maintaining an atmosphere that can support life. Without the magnetopause, Earth's atmosphere would be more vulnerable to being stripped away by the solar wind. In fact, scientists speculate that the presence of a magnetic field may be a prerequisite for a planet to support life. This hypothesis is supported by the study of Venus and Mars, where the absence of a strong magnetic field has had a significant impact on their atmospheric conditions and potential for hosting life. The magnetic shield of Earth has allowed life to flourish by protecting the planet from cosmic radiation, solar wind, and other forms of space weather. Without this shield, the surface of Earth would be bombarded with radiation, making it difficult, if not impossible, for life to survive. The magnetopause's interaction with the solar wind ensures that harmful particles are deflected, keeping Earth's environment stable and conducive to life. In addition to its direct impact on Earth, the magnetopause has broader implications for space exploration and our understanding of the universe. As humanity continues to explore the outer reaches of space, we must consider how to protect both our technology and our future colonies from the dangers of solar wind and space radiation. The research into the magnetopause offers valuable lessons on how to harness the power of magnetic fields to safeguard human life beyond Earth. Understanding the magnetopause also informs the search for life beyond our planet. The study of exoplanets, or planets outside our solar system, has become a key focus for astronomers looking for signs of life. Planets with strong magnetic fields, much like Earth's, may have a higher likelihood of supporting life because they offer protection from harmful solar radiation. As telescopes become more advanced and we continue to discover new exoplanets, the magnetopause's role in shielding planets will be an important factor in determining which worlds may be habitable. One of the most intriguing aspects of the magnetopause is the mystery of its formation and evolution. How did Earth's magnetic field develop, and what role did it play in the early history of our planet? Scientists are still working to answer these questions, but the magnetopause's formation likely began early in the planet's history, as Earth's molten core began to cool and generate a magnetic field. Understanding the history of the magnetopause could provide valuable insights into the formation of planetary magnetic fields and the conditions necessary for life to take root on a planet. As research continues, the magnetopause will undoubtedly remain a central focus for scientists studying space weather, planetary magnetism, and the broader processes that govern our solar system. From protecting Earth's technological infrastructure to understanding the evolution of planets, the magnetopause offers a wealth of knowledge about the forces that shape our world and the universe. The magnetopause is more than just a shield. It represents a dynamic zone of interaction between Earth's magnetic field and the solar wind, with ever-changing conditions that influence both our planet and the surrounding space environment. As scientists continue to investigate this boundary, they uncover increasingly complex relationships that expand our understanding of space weather, solar dynamics, and planetary protection. What's truly fascinating is how the magnetopause responds to various solar conditions. The Sun doesn't produce a constant flow of solar wind, it operates in cycles, ranging from calm periods to intense solar activity, including solar flares and coronal mass ejections, CMEs. During periods of intense solar activity, the solar wind becomes more energetic, increasing the pressure exerted on the magnetopause. This pressure can cause the magnetopause to expand, shifting its location farther from Earth. In extreme cases, if the solar wind's energy becomes powerful enough, it may compress the magnetopause closer to the Earth. These interactions demonstrate the delicate balance that exists between our planet and the solar wind, a balance that can fluctuate over time and have significant consequences for the space environment. One area of particular interest is how the magnetopause responds to CMEs. When a CME erupts from the Sun, it releases a massive burst of charged particles, which can travel through space at high speeds. If these particles reach Earth, they can interact with the magnetopause, causing geomagnetic storms. These storms, although fascinating to scientists, can have serious consequences on Earth's technological systems. For instance, satellites may experience disruptions, and power grids on Earth can suffer from voltage surges or even complete failures. A notable example of this is the 1989 geomagnetic storm, which caused a massive power outage in Quebec, Canada. This event underscored the importance of understanding how the magnetopause functions and how it can protect Earth from these potentially catastrophic events. Interestingly, the magnetopause also plays a significant role in shaping the behavior of Earth's auroras. These stunning light displays, commonly known as the northern and southern lights, occur when charged particles from the solar wind interact with Earth's magnetic field. As the solar wind reaches the magnetopause, it is deflected and funneled along magnetic field lines toward the poles. There, the particles collide with atoms and molecules in the Earth's atmosphere, releasing energy in the form of light. The result is the mesmerizing auroras that can be seen in the polar regions. The magnetopause, therefore, doesn't just protect Earth, it also contributes to some of the most beautiful natural phenomena on the planet. Moreover, the magnetopause plays a pivotal role in shaping the behavior of space weather events that influence the entire solar system. While Earth benefits from its strong magnetic field, other planets in the solar system experience vastly different conditions. Take Jupiter, for example. Jupiter has an enormous and powerful magnetosphere, much larger than Earth's. In fact, the size of Jupiter's magnetopause is so great that it extends beyond the orbit of its moon, Ganymede. This colossal magnetosphere shields Jupiter and its moons from the solar wind and cosmic radiation in ways that Earth's magnetosphere does for our planet. But Jupiter's magnetosphere also serves as a window into understanding how powerful magnetic fields interact with the solar wind on an even grander scale, providing invaluable insight into the dynamics of planetary protection. In comparison, Mercury, the closest planet to the Sun, has a very weak magnetic field and no true magnetosphere. As a result, it lacks a protective shield against the solar wind. Without a significant magnetic field to form a magnetopause, Mercury's surface is exposed to direct bombardment from solar particles. This situation has led to the stripping away of Mercury's atmosphere over billions of years. Despite its proximity to the Sun, this lack of protection makes Mercury a hostile environment for life, reinforcing the crucial role of the magnetopause in maintaining planetary conditions suitable for habitability. The comparison between Earth and other planets emphasizes the magnetopause's vital function. While planets like Venus and Mars lack strong magnetic fields, Earth benefits from a robust magnetic shield that ensures the stability of its atmosphere, protecting life as we know it. This balance between the solar wind and the magnetosphere is not just a cosmic curiosity, but a critical factor in the preservation of life on our planet. The magnetopause's role in safeguarding Earth is an extraordinary testament to the complexity of the forces that govern our solar system, highlighting how interdependent our planet is with its cosmic environment. As we venture beyond Earth's magnetopause, scientists also explore the potential for establishing magnetic shields for spacecraft and future space colonies. The concept of building artificial magnetic fields to protect astronauts from space radiation has become a focal point of space research. If we are to send humans on long-duration missions to destinations like Mars or establish colonies on the Moon, protecting these pioneers from the Sun's radiation is a top priority. This concept is currently in the experimental stages, but the lessons learned from studying Earth's magnetopause could pave the way for the development of protective technologies for human exploration beyond the safety of Earth's magnetic field. One of the more fascinating aspects of studying the magnetopause is the influence it has on the magnetospheres of other celestial bodies. For example, the magnetosphere of Saturn's moon, Titan, is of particular interest to researchers. Titan, although it doesn't have a magnetic field of its own, is influenced by the magnetopause of Saturn's enormous magnetosphere. The interactions between Saturn's magnetosphere and Titan's atmosphere have become a key area of study, as they provide clues about the role of magnetic fields in shaping atmospheric and space weather dynamics on distant worlds. Titan's example is a reminder that even in a distant part of the solar system, magnetic fields play an integral role in planetary systems. While Titan is far removed from Earth, the study of its interaction with Saturn's magnetosphere can help us understand how magnetic fields influence other moons, planets, and bodies in space, shedding light on the conditions necessary for life to potentially exist in the vastness of the cosmos. Another exciting frontier in space exploration is the discovery of exoplanets, planets outside our solar system. These planets, orbiting distant stars, may have magnetic fields that protect them from the solar wind, just like Earth. In fact, the presence of a magnetic field on an exoplanet could be one of the key factors in determining its habitability. If the magnetic field is strong enough to create a magnetopause and shield the planet from harmful radiation, it could potentially support liquid water and, by extension, life. As scientists search for exoplanets in the habitable zone of their stars, regions where liquid water could exist, understanding the importance of a magnetopause becomes increasingly crucial. If we find exoplanets that have both the right conditions for liquid water and a protective magnetic field, we may have found the perfect candidates for life beyond Earth. The magnetopause could be the key to answering one of humanity's most profound questions: are we alone in the universe? The study of Earth's magnetopause and its relationship with the solar wind opens doors to an entirely new understanding of planetary science. As we continue to study this boundary, we deepen our knowledge of how magnetic fields influence planetary evolution, space weather, and the potential for life beyond Earth. The magnetopause is not just a protective shield for our planet, it is a gateway to understanding the complex interactions between stars, planets, and the cosmic forces that shape the universe. Whether it's shielding Earth from solar wind, guiding the path of charged particles, or contributing to space weather, the magnetopause plays an indispensable role in the intricate balance that sustains life on Earth, and potentially, life elsewhere in the cosmos. The magnetopause is a crucial part of our planetary defense, but its significance goes beyond protecting Earth. It provides a unique environment where scientists can observe how charged particles behave when subjected to the influence of magnetic fields. This area of study offers new insights into not only planetary physics but also how other celestial bodies interact with their environments. As our technology advances, so too does our ability to explore this mysterious boundary with greater precision and depth. The first step in understanding the magnetopause was made possible by a series of space missions dedicated to studying Earth's magnetic field and the solar wind. The NASA missions, such as the Magnetospheric Multiscale (MMS) mission, provide a detailed view of the magnetosphere's structure. This mission, launched in 2015, consists of 4 spacecraft flying in a coordinated manner to study the magnetopause and its role in the movement of charged particles through space. The spacecraft use a combination of instruments, such as electric field detectors and particle analyzers, to measure the conditions around the magnetopause and map how it responds to changes in the solar wind. This real-time data is crucial for understanding the intricate processes happening in this zone and helps scientists predict how solar storms might impact Earth. One of the most important contributions of the MMS mission is the discovery of the phenomenon called magnetic reconnection. This process occurs when magnetic field lines in space snap and reconnect, releasing huge amounts of energy in the form of plasma. Magnetic reconnection is a fundamental process that takes place in many regions of space, including the magnetopause. The energy released during magnetic reconnection can accelerate charged particles, creating space weather phenomena such as geomagnetic storms and auroras. By studying this process, scientists can better understand the dynamics of the magnetosphere and how it responds to changes in the solar wind. The MMS mission has provided valuable insights into this complex process, revealing how magnetic field lines interact and how energy is transferred across the magnetosphere. The magnetopause's influence extends far beyond Earth's atmosphere. It has far-reaching effects on space weather that can impact satellites, communications, and even power grids. For instance, solar storms that emanate from the sun can cause sudden fluctuations in the solar wind, which are carried through space and interact with Earth's magnetopause. If the magnetopause is unable to effectively shield Earth from these high-energy particles, they can enter the atmosphere and cause geomagnetic storms. These storms can disrupt satellite operations, GPS systems, and communication networks, making them a serious concern for modern technological infrastructure. The magnetopause also plays a key role in protecting Earth's ionosphere. The ionosphere, a layer of the Earth's atmosphere that contains charged particles, is essential for radio communication and GPS. During solar storms, the ionosphere can become heavily disturbed, resulting in radio blackouts and interference with satellite signals. By preventing the solar wind from directly impacting the ionosphere, the magnetopause helps to maintain the stability of communication systems, ensuring that these essential technologies continue to function smoothly. This is particularly important for navigation systems, as GPS relies on a stable ionosphere to provide accurate location data. Any disturbance in the ionosphere can lead to inaccuracies in GPS positioning, which can have far-reaching effects. Understanding the role of the magnetopause in space weather is also crucial for preparing for potential future missions to the Moon, Mars, and beyond. Astronauts venturing into space will face challenges from solar radiation that are very different from those experienced on Earth. While the magnetopause offers protection to Earth, the astronauts will not be able to rely on it once they venture beyond the planet's magnetosphere. Space agencies are actively researching ways to create artificial magnetic fields or other protective systems to shield astronauts from harmful solar radiation during long-duration space missions. By understanding how the magnetopause works, scientists can use this knowledge to design better protective measures for space travelers, ensuring their safety during deep space missions. As we explore more of the solar system, we may discover that other planets or moons have their own versions of the magnetopause. For instance, scientists are keenly interested in studying the magnetospheres of distant exoplanets. Many of these exoplanets may be located in the habitable zones of their stars, where conditions could allow for the presence of liquid water and possibly even life. However, a planet's magnetic field is critical in determining whether it can protect its atmosphere from solar and cosmic radiation. Without a magnetosphere, a planet is vulnerable to the stripping of its atmosphere, making it less likely to support life. Studying the magnetospheres of exoplanets will be crucial in identifying planets that may harbor the conditions necessary for life. One of the most exciting aspects of space exploration is the search for life beyond Earth. While we've yet to discover definitive evidence of extraterrestrial life, the study of magnetic fields and their role in planetary protection could play a crucial part in finding habitable planets. In the quest to understand whether other worlds might be capable of supporting life, the magnetosphere could provide important clues about a planet's potential to sustain life. Planets with strong magnetic fields may have a better chance of maintaining a stable atmosphere and protecting any potential life forms from harmful radiation. As technology improves and we gain the ability to detect the magnetic fields of distant exoplanets, the magnetosphere will become a key factor in identifying promising candidates for life beyond Earth. Our exploration of the magnetopause is not just about understanding the forces that protect Earth. It's about learning how to protect ourselves as we venture farther into the universe. The magnetopause serves as a reminder of the power and complexity of the forces at work in space, and how crucial it is to study and understand these forces as we continue our journey into the unknown. Whether it's shielding us from solar storms or providing insights into the conditions necessary for life elsewhere, the magnetopause plays a vital role in our exploration of the cosmos. It's a reminder that the forces that shape our planet are not isolated but are part of a larger, interconnected system that extends across the universe. Through continued research and exploration, we'll uncover even more secrets about the magnetopause and its role in the cosmic balance. As we learn more, we'll be better equipped to navigate the challenges of space exploration, ensuring that humanity can thrive in the vastness of the universe. The magnetopause, while invisible and often overlooked, is one of the most important guardians of life on Earth, and its study will continue to reveal new insights into the intricate and fascinating workings of our solar system and beyond. In the grand scheme of things, Earth's magnetopause is just one of many fascinating features of our planet that have enabled life to thrive. However, as we continue to explore space and investigate phenomena beyond our planet, the magnetopause will undoubtedly remain one of the key topics in understanding how planetary systems function, how cosmic radiation affects planets, and how we can better safeguard human civilization against these unseen forces. The magnetic field, although invisible to the naked eye, is the guardian of life on Earth, shielding us from the harsh conditions of space. Its importance cannot be overstated, and its study offers a glimpse into the broader workings of the universe. Moreover, the Earth's magnetosphere, including the magnetopause, is not a static entity. It is constantly shifting, influenced by the solar wind and the sun's ever-changing activity. During times of solar maximum, when the sun is most active, the solar wind is stronger, causing the magnetosphere to contract. Conversely, during solar minimum, when solar activity is at its lowest, the magnetosphere can expand. This dynamic nature of the magnetosphere is a reminder that space weather is a constantly evolving phenomenon that can have far-reaching effects on both Earth's environment and our technological infrastructure. The fluctuations in the magnetosphere also raise questions about how life on Earth has adapted to such changes. While the magnetopause provides a protective shield, it's not a guarantee against every solar event. Powerful solar flares, which release immense amounts of energy into space, can still have a significant impact on Earth, even if the magnetopause is functioning normally. These solar flares can trigger geomagnetic storms that, although less damaging than the solar wind itself, can still disrupt satellite communications, navigation systems, and power grids. In extreme cases, they can even pose a danger to astronauts in space. As we rely more heavily on technology and space-based infrastructure, understanding how these solar events interact with Earth's magnetic field becomes increasingly important. It's also worth considering the relationship between the magnetosphere and Earth's atmosphere. The magnetosphere helps to prevent the atmosphere from being stripped away by the solar wind, a process that is crucial for maintaining the conditions necessary for life. Without the magnetosphere, the solar wind could gradually erode the atmosphere, just as it has done to other planets in our solar system that lack a strong magnetic field, such as Mars. This means that the magnetopause plays a role not just in protecting us from solar storms, but in maintaining the long-term habitability of Earth itself. It acts as a barrier, allowing the atmosphere to remain intact and preserving the delicate balance of gases necessary for life. This delicate balance is further complicated by the fact that Earth's magnetosphere is not perfect. While it does an excellent job of deflecting most of the solar wind, there are still instances where charged particles penetrate the magnetopause and reach the atmosphere. When this happens, the particles can interact with the gases in the upper atmosphere, creating auroras, the beautiful, colorful displays of light that we associate with the northern and southern lights. These auroras are a visual manifestation of the magnetosphere's interaction with the solar wind, a reminder of the dynamic forces that shape our planet's environment. But what if we could observe the magnetopause from a different perspective? What if we could witness the powerful forces of solar wind colliding with Earth's magnetic field in real time? Thanks to space exploration, we're able to do just that. Spacecraft like the MMS mission and the Voyager probes have allowed scientists to observe these interactions firsthand, providing valuable data that expands our understanding of the magnetosphere and the magnetopause. These observations not only give us a better understanding of Earth's protective shield but also offer insights into similar processes occurring around other planets and stars. In the broader context of space exploration, the magnetopause also highlights the importance of understanding space weather. As human activities in space increase, whether it's sending astronauts to the Moon, Mars, or even deeper into the cosmos, ensuring the safety of astronauts and space-based equipment will be critical. The magnetopause and the space weather associated with it will play a pivotal role in this endeavor. In particular, understanding how the magnetopause shields the planet from cosmic radiation can help us design better spacecraft and protective measures for future missions. While Earth has the advantage of its natural magnetosphere, human-made solutions will be necessary to protect astronauts from space weather as they venture farther from home. For example, radiation from the Sun and other cosmic sources presents a significant risk to astronauts, particularly those on long-duration missions. Without a magnetosphere to shield them, astronauts will be exposed to far higher levels of radiation than they would experience on Earth. This radiation can cause a range of health problems. To mitigate these risks, space agencies are exploring ways to protect astronauts by creating artificial magnetic fields or designing spacecraft that can shield against radiation. The knowledge we gain from studying Earth's magnetopause can directly inform these efforts, helping to protect human life as we expand our presence in space. Beyond space exploration, the magnetopause serves as a reminder of how interconnected the universe is. Every celestial body, from the Sun to distant exoplanets, interacts with its environment in ways that shape the conditions of life or the absence of it. The study of these interactions, particularly the role of magnetic fields in planetary protection, will continue to play a key role in our understanding of the cosmos. As we learn more about Earth's magnetopause, we gain a greater appreciation for the delicate balance of forces that allow life to exist on our planet. At the same time, we are preparing ourselves for the challenges that lie ahead as we look to explore other worlds and potentially make them habitable. Through continued research and exploration, we are only beginning to scratch the surface of the many mysteries surrounding the magnetopause and its role in safeguarding Earth. As technology advances and we gather more data from space missions and satellites, we will continue to uncover new insights into this fascinating boundary. The magnetopause is not just a physical barrier, it's a symbol of the invisible forces at work around us, forces that have protected and shaped life on Earth for billions of years. Understanding these forces is key to ensuring that humanity can continue to thrive on our planet, and eventually, venture safely into the stars. As we continue to push the boundaries of space exploration, our understanding of the magnetopause will only grow. With every mission and every new discovery, we unlock more of the secrets that lie hidden in the depths of space. And in doing so, we are reminded of how much we still have to learn about the universe and the forces that govern it. The magnetopause is just one piece of the puzzle, but it is a crucial one, a piece that helps protect us from the dangers of the cosmos and guides us as we explore new frontiers in the search for knowledge and discovery. As our understanding of the magnetopause deepens, it becomes increasingly clear that this boundary represents more than just a shield against cosmic threats. It is an essential component of the Earth system, a dynamic interaction between solar energy and the planet's magnetic field that sustains the conditions required for life. This interaction is not just important on a scientific level but on a practical one as well. As space exploration evolves and humanity begins to consider longer-term ventures into deep space, the magnetosphere serves as a reminder of the fragility of the environments we rely on, both on Earth and in outer space. In fact, some of the most exciting research into the magnetopause is happening right now, as scientists continue to study its behavior in the context of human activity and the broader universe. One of the central questions in this research is how other planetary bodies might cope with similar forces. Earth is unique in its magnetic field's effectiveness, but the magnetosphere is not guaranteed on other planets, especially those located outside of our solar system. By studying Earth's magnetopause in greater detail, we can begin to infer how other exoplanets might fare in the face of their own solar winds, helping us understand whether these distant worlds could support life. The study of magnetospheres is critical for understanding planetary habitability. Planets without a strong magnetic field, like Mars, offer a cautionary tale of what could happen if a planet loses its protective magnetic shield. Over time, solar winds strip away atmospheres, leaving planets barren and uninhabitable. The ancient history of Mars serves as a reminder that a planet's magnetic field is vital for maintaining the conditions necessary for life. In this sense, the magnetopause isn't just protecting us, it is ensuring that Earth remains a sanctuary amidst the vast emptiness of space. As we study our own magnetosphere, we may uncover vital clues about the fate of other planets that could potentially support life. Another fascinating aspect of the magnetopause is its role in the broader context of space weather. This term is often used to describe the various conditions and phenomena that arise from the Sun's interactions with the Earth, including solar flares, coronal mass ejections, and the solar wind itself. These space weather events can have dramatic impacts on both our daily lives and our long-term infrastructure. The magnetopause plays a crucial role in mitigating the worst effects of space weather, but its ability to do so is not infinite. Powerful solar storms, for example, can overwhelm the magnetopause, leading to geomagnetic storms that disrupt satellites, communications, and even power grids on Earth. These storms, while not life-threatening in the traditional sense, highlight the need for continuous monitoring and research into space weather. Space agencies and research institutions around the world are increasingly investing in ways to better predict and understand these space weather events. By studying the magnetopause and the interaction between the solar wind and Earth's magnetic field, scientists can improve their ability to forecast geomagnetic storms and take proactive measures to protect vulnerable systems. One of the biggest challenges is predicting the exact timing and strength of solar flares and coronal mass ejections. These events are often sudden and unpredictable, making it difficult to assess their potential impact on Earth's infrastructure in real time. But by analyzing the data gathered from satellites and space-based observatories, researchers are making significant strides in improving their forecasting models. The effects of geomagnetic storms are more than just theoretical. In 1989, for example, a massive solar storm knocked out power to millions of people in Quebec, Canada. The storm caused widespread electrical failures, and power companies had to scramble to restore service. More recently, in 2003, a series of solar flares and coronal mass ejections caused a temporary disruption in satellite communications and GPS systems, highlighting the vulnerability of modern technology to space weather. These events serve as a reminder that the magnetopause, while protective, cannot completely shield us from the full force of the Sun. As our reliance on technology continues to grow, understanding and preparing for these space weather events becomes an ever more pressing concern. In the future, as humanity ventures farther into space and establishes a permanent presence on the Moon or Mars, the role of magnetic fields will become even more important. On the Moon, for instance, there is no global magnetic field to protect against solar wind, leaving astronauts exposed to higher levels of radiation. This is one of the challenges that scientists and engineers are grappling with as they design habitats for lunar and Martian colonies. The lessons learned from studying Earth's magnetopause could help inform the development of artificial magnetic shields or radiation-hardened infrastructure that will provide similar protection for astronauts and equipment. The magnetopause also plays a crucial role in space weather's influence on the Earth's atmosphere. While the magnetosphere protects us from direct exposure to harmful solar radiation, there are still secondary effects that manifest within the atmosphere. The interaction of solar wind with Earth's magnetic field can create disturbances in the ionosphere, a layer of charged particles high above the Earth's surface. These disturbances, in turn, can affect radio signals, GPS systems, and even power grids. When a particularly intense solar storm occurs, the ionosphere can become overloaded with energy, leading to widespread disruptions in communication and navigation systems. In addition to these technical concerns, the magnetopause and its interaction with solar wind are also linked to one of the most awe-inspiring natural phenomena visible from Earth, the auroras. When charged particles from the solar wind interact with the Earth's magnetic field, they are funneled toward the poles, where they collide with atoms in the atmosphere, causing them to emit light. This process creates the stunning aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. These vibrant light displays are a beautiful reminder of the powerful forces at play around us, and they highlight the incredible interplay between the magnetopause, solar wind, and Earth's atmosphere. As we continue to explore the mysteries of space and the forces that shape our planet, the magnetopause will remain a critical area of research. Its dynamic nature, protective role, and importance for life on Earth make it one of the most fascinating and essential features of our planet's environment. But as we reach for the stars and look to other worlds, the lessons we learn from studying Earth's magnetic field will shape our future in space. Understanding how planetary magnetic fields protect life and the technologies we depend on will be vital as we venture farther into the unknown. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.